Okay. Thank you everyone for being here, and thank you, Clément, for flying all the way from France to teach us about the frontiers of difference and difference. So today, this is a part of a, 2.5 day course. I guess we already did 1 hour before online, and we'll have a 9 to 3 classes today and tomorrow. And we have 9 to 10:30 lecture, then we'll have a half an hour coffee break, then lecture, and then 12:30 we'll have lunch at the private dining room. And tomorrow is the same. And from 3 to 5, we'll have office hours in the same room. So whoever has any questions, just feel free to stay back. And as for the online participants, we just raise your hand if you have a question. And Claudia is moderating the session. She can unmute and can ask questions. And for the rest of us, jump in whenever. With that, the floor is yours. Thank you very much.
Thank you very much. Thanks, Devaki. Thanks, everyone, for coming. So, is the screen big enough? I should make it a little bit bigger, actually. So, for those, so last time when we during the Friday lecture, we started by giving an intro to classical diffs, where we have a binary treatment and no variation in treatment timing. And so that's even those pretty simple designs. Actually, when it comes to estimating event-steady effects and the effect of having been exposed to the treatment for 1 period, for 2 periods, etc., we can actually use at least 2 unbiased estimators. The coefficient on an indicator for having been exposed to treatment for L periods in a 2-way fixed effects regression, or this less standard estimator, where rather than using the period just before treatment onset as the reference period, we use an average of all untreated periods. Okay, and this estimator can be obtained via a 2-way fixed effects regression, where omit from the regression all the period for all the time periods prior to treatment, rather than just omitting period F. And we saw that under parallel trends and no mutation assumptions, that estimator is also a valid bias estimator of the effect of L periods of exposure. So when we have 2 not numerically equal unbiased estimators of the target, which criterion should we use to decide which estimator we want to use? So the 2 estimators as GMM estimators, yes. But and so what when you think of GMM? What is the nice thing about GMM? Yeah, we're going to need to think about the correlation of errors, because that's going to influence what? Yeah, exactly. So, and because the 2 are unbiased, there is actually variance. Okay, so when we have 2 unbiased estimators of the same target, then we start looking at variance to choose the estimator with the lowest variance. So why do we index this estimator by DL? Well, that's actually because this estimator that have been proposed by 3 papers at the same time, Borosiak and co-author, Liu and co-author, Gardner and co-authors, in the context of binary and staggered designs, those imputation estimators. When we actually go back to classical design without variation in timing, they reduce to those simple estimators here. Okay, and the estimators of Callaway, Stone, and Abraham, they actually reduce to the 2 ways to the beta L estimator we saw coefficient from the standard 2-way fixed effects regression. And so then it becomes interesting to compare variance of those estimators in a very simple design, because maybe then we learn useful lessons for the more complicated designs with variation in timing. And so the headline result of the paper by Borussia et al. Was the following. So you remember that under a parallel trend assumption, we have our expected outcome without treatment can be decomposed into a group fixed effect and a time fixed effect. Now I can let epsilon denote different someone's actual outcome and their expected outcome, which is just error, a stochastic error, if you want. And then with those, I can say that my untreated outcome is the sum of the group fixed effect, the time fixed effect, and an error. And so in Teketa, so that if those errors are independent both across groups and areas and identity distributed, then their estimator is actually the best linear unbiased estimator of the effect of being exposed to treatment for L periods. And then the standard study estimator is also a linear estimator that's also unbiased. Then that must imply that there is a lower variance than the standard estimator, which turns out to also be the Callaway and Santana or Stone and Abraham estimator in a very simple design. Now, these results type very assumption. Okay, it assumes in particular that the errors are dependent not across groups, which is an assumption we've been kind of okay making so far, assuming that California and Michigan are independent of each other, which is probably not very realistic, but that's the type of assumptions we're going to be making. But here you assume that the errors fixing G are actually also independent across T. Okay, that the shock at period 1 is independent of the shock received at period 2, etc., which is really even realistic. Okay, that's clearly the type of assumptions we would prefer not to make. So now, of course, like when you try to compare the estimators' variances, you'll make this type of very assumptions, because otherwise, without the strong assumptions, the variances never simplify enough that you can draw these comparisons. So now the question is really, is this just a simplifying assumption that allows us to make a comparison, but the assumption is violated, the order of the variances still more or less hold, or does the ordering of the variances really relies on this assumption? And actually the answer, coming from a recent paper by Harmon, shows that it's the second. It's that the result that the Borussia, Liu, and Gardner estimator has lower variance than the other estimators, that crucially relies on the assumption that are easy. And so Harmon actually shows that to make the other type of assumption, namely that errors follow a random walk, so meaning that errors are extremely persistent over time, then you get the opposite result. You get that actually the group estimator is the standard event study estimator. Turns out the Callaway Santana and the Sunan Abraham estimator in more complicated design. Okay, and then in that case, you have that under random errors, then the Borussia et al. Estimator has a greater variance than the standard estimator. So I'm going to try to give a bit of intuition, because intuitively, for people that have my generation, I guess, of researchers who've not studied enough time series and old school panel data as perhaps they should have, when you see an estimator like this one, you're thinking, of course, this one is going to be more efficient, right? It's using more data to reconstruct the base outcome than the standard estimator. Using more data can never hurt. It should always increase statistical precision. Well, that kind of reasoning is a reasoning that's implicitly assuming that everything is dependent. But if you actually have very strong correlations, using more data hurt you. And because I had to persuade them of that, and I read Harmon paper, I came up with a very simple real example, where we assume that we have only 3 time periods, and the treatment starts at period 3. Okay. So then the difference between the standard event study estimator and the Borussia estimator at and when I mean eta, like not only the co-author of OSAC, but the other 2 papers. So that it's going to take rather taking differences between Y3 and Y2 is going to take differences between Y and the average of YG2 and Y1. Okay, and now Y3 depends on the period 3 error, but here take averages of and the period 1 error, and then under our under error assumption, get that epsilon G3 is epsilon G2 plus G3, and epsilon G2 is epsilon G1 plus UG2, etc. And so when you plug in those expressions, you get the expression here. You get that this difference here is going to depend on the period 3 idiosyncratic error plus a half of the 2 idiosyncratic error. While when you do the same thing, the same computation, but for the differences involved in the standard estimator, where you only compare outcome evolutions from period 2 to period 3, now you see that only stochastic component is UG3. And then, of course, the variance of 3 plus a half is going to be greater than the variance of UG3. So that's effectively why we end up with more noise by why we are effectively using more data. So that means that essentially now the standard statistical approach to comparing estimators is not very helpful, because we have estimators that are unbiased under the same assumptions, and then variance, well, it depends. It depends on the nature of the error. If you ask a researcher, do you think that your error is likely to be IIT or random walk application, they just don't go. And so that's not very, that's not the type of on which it's really easy to take an ex-ante stance. So then another approach is less to try to discriminate the 2 estimators, but which is less standard in terms of statistical theory, but which is, I think, also useful, is to ask, okay, but what if our parallel assumption and non-anticipation assumptions under which the 2 estimators are unbiased were not hold exactly? And I think it's the thought experiment that's actually useful, because we are not in an RCT where we know that by design treated and control are identical. We are natural experiment where we make anticipation and parallel trend assumption because that perhaps they are not bad first order approximations of what's going on, but they might not hold exactly. Okay, we might have differential trends, for instance. So then, so actually, I'm going to do a question. So, what is looking at the expression of this estimator here and thinking of the expression for the other is exactly the same, except that here you just have YT F minus 1. Which of the 2 estimators would be more biased under, let's say, a violation of parallel trends or a violation of the no anticipation assumption? It depends on when it's violated. Exactly. And so, so this one less biased if we have violations when. Yeah, exactly. And so here I think a good representation is to say that this one here is going to be more to violations of the no assumption, because if you have anticipatory effects, they are most likely going to happen either in period F minus 1 or let's say F minus 2, right before the event. And then estimator is going to be more robust to that, because the base formed not by only F minus 1, but or F minus 2, but taking an average across all unbiased, okay? While the other estimator, in all on the edge of the event, would be really severely affected by anticipation effects. Now, contrary, if you believe that you have, for instance, differential linear trends between the treatment and the control group, then those differential trends are going to be widening the longer the horizon over which you're comparing the treated and the control, right? And then this estimator will be more biased because the other one, the baseline is f minus 1, so you're making comparison from f minus 1 to f minus 1 plus L over L period. When one, the baseline is, roughly speaking, minus 1 plus 1 divided by 2, so f divided by 2. So making comparison from f divided by 2 to f minus 1 plus L, which is over longer horizon. Okay. So now and here is my take on this. My take that, because again, then helpful because you know it depends. So is that it's a little bit easier for applied researcher to immunize themselves against anticipatory, for instance, by finding the date of the as the date when the treatment was announced, while immunizing yourself against different trends, differential trends that are not big enough for pre-trends test to detect them, but that might still be there in your data is harder. Okay, and so the bottom line. So our recommendation at the end, which again others disagree with, is to stick to the two-way effect event study estimator. Also, think that the two estimators under parallel trend and anticipation are biased for the same target parameter. So in principle, they should not really using one or the other should never make a difference. If it does actually make a big difference, then that means that your design is invalid, that non-anticipation and parallel trends are violated. Yeah?
This is all based on f&I arguments. So, right? So, if we're worried also that we don't have like too many cross-sectional units and we're worried about small sample performance as well, then how do you see this? Because I guess there I see more benefit to potentially not overweighting a very noisy last period.
So the arguments are not really asymptotic. Actually, it's like finite sample variance, finite sample bias. But yeah, then again, actually, like under wrong errors, actually it's better to put all on the single data point prior to the event than averaging all the treatment periods. Even though it's very in the end, you're going to end up adding more noise by doing this averaging. So it depends on the correlation structure of the error. So something that's not really been done yet, even though both will discuss it a little bit in their web appendix, is to say, okay, so now actually let's first estimate. Let's assume that our errors follow on AR1. Which nest, IID nest with a coefficient of 0 or random walk with a coefficient of 1. Let's estimate the coefficients in this AR1, and then let's use the estimator that's the most efficient given the actual correlation structure we have in our in our data. That perhaps that's something that could be done. I don't know if it's so. My sense is that at the end of the day, it's in most applications, it's never going to bring very large precision improvement. Maybe there exists some applications where that does, but that it's intuitively I would say it's unlikely to be like the most frequent case. And so at this stage I don't think there is occasion to worry too much about that. And yeah. Okay, so the last thing I want to say very I'm not going to go over all this, but about classical designs is the issues with parallel trends test. So this recent literature, there is one strand of literature that says that standard methods are not robust when you face heterogeneous treatment effects. Then there is a very important strand that says that people have tended to believe that when they even steady regression or run an F test on the pretrends coefficient, don't reject the null that all the pretrends are 0, then it's fine. They can go on and assume that they have a valid design. When there is a literature that challenges that view, and it's based on these very, very simulations where Roth, A.R. Insight's paper, review 12 papers published in AER, AJ Applied, AJ Policy. And so the squares are pure average effect estimates in those papers. And the green circle represent the bias that we generate in this estimate by linear differential trends between the treated and the control group that at least would have had only 50% chances of detecting given the standard error of their pre-trend coefficient. And so what this is saying is that so we find an average estimate of roughly 5. When it's saying that with differential trends that we could have had only 50% chances of detecting, those differential trends are enough to generate a bias of 3 in this coefficient of 5, meaning that perhaps 60% of what we think is a treatment effect could actually just by differential trends that are pretest were underpowered to detect. Okay, and it's an issue that is very important in some, not in all of the papers. So, for instance, when you look at this paper, the actual treatment effect estimate is much larger than the bias that could be due to differential trends. That's also the same for that paper. For that paper, for instance, it's not that bad, but there are quite a few published papers where more than 50% or all of the actual treatment effect could be due to just differential trends that were underpowered to reject. Okay, so now move to we're going to be talking about binary and staggered designs. Okay, so what do we mean exactly by binary and staggered design? So it means that we have groups that into the tree, but at heterogeneous states. Not all treated groups get treated at the same state. That's going to be the only with respect to the previous designs we considered. We still have binary treatment. We still treatment is still absorbing. Once you're treated, you cannot go back to being untreated. The only difference is that the treated can start getting treated at different days. So we might have never treated. So we're going to let FG denote the first date at which group G gets treated. Okay, now for universal F, because every group got treated at the same time. Now the first date becomes group specific, and we might have a pure group never get treated, and we let FG equal to 50 plus 1 for them, just a convention. So our running example. So we're going to do 2 examples in this chapter. One, the we're going to do the replication on state edge everyone at the end, for which I will show you the results. And so the first one is looking at the effect of unilateral divorce laws on divorces. So the design is as follows. So we have 29 US that adopt lateral divorce law at some point between 68 and 88. So one first does pure US states panel data across all these years to estimate the effect of those laws on the divorce rate, and that's a treatment that satisfies this definition here. It's a binary. It's absorbing no state has reverted a unilateral divorce law, but the treated states get treated at different time periods. So normally you should have should have access to this data set through the link. So all of you already have it on your computer. So here we have a state identifier, a year identifier, cohort identifier, and the year AG after the treatment. So that our notation. The only difference being that for never state, it's going to be more to let the cohort variable be equal to 0 rather than +1. Then we created an early later variable taking 3 values, 0, 1, 2, 1, 2, 3. 3 is for the never adopters, and then 1 and 2 are going to distinguish between the adopters, those that adopt before the median and after the median year. UDL is 1 if state 3 has a UDL is 0 otherwise. Exposure length is for any GT cell, the number of time periods of years for has been exposed to UDL, so 1 in the adoption year, 2 in the year after adoption, etc. So the real time 1, real time 15 are, the relative indicators that we put in our event study regression. So indicator is equal to 1 is equal to FG minus 1 plus L. Then we do what's called endpoint binning, namely don't include those indicators for any exposure lengths and that exist in our data, but for when a state has been exposed to the DL for at least 16 years, and then we put all of those exposure lengths together. Then for our placebo, we have relative times for before being treated by DL, and there are some endpoint binning. And finally, the outcome is the divorce rate in stage G and ERT. And importantly, we're going to weight all of by the population stage G in T, because perhaps you don't want to put to put the same weight and effect estimation to California and to Arkansas. And finally, we have state population in 1968, which is the last year before the state started adopting UDL, so it's a bit our baseline year. And we have a variable for the never treated groups. So first, we're going to generalize our parameter. So as before, we have specific effects first. So we're going to define TGT by the expectation of the difference between the actual outcome of group G at time T and their never treated outcome. And we define those effects only for the treated set, otherwise this difference is just 0. And for and so that we have observed outcome is YGT of 0 FG minus 1 because the set untreated for FG minus 1 period. And then we have that number of 1 here. So could someone try to interpret this EGT? Yeah, exactly. So it's an effect of being exposed to a treatment for that number of time periods. Exactly. So then we can generalize our ATT effect by just taking the TGTs for all the treated cells, and then we just average them. And then we are going to do a simple change in variable and define TGL and treat R, okay, that it's an effect in relative time, as YG FG minus 1 plus L minus YG FG minus 1 plus L under L periods of treatment or no treatment at all. Okay. And we have that this is just TG at FG minus 1 plus L. So it's just a convenient notation to index treatment effects by length of exposure rather than calendar time. So then once we have notation, we can redefine our TL effect. We are to look at, we're going to average the effect of L periods of exposure to treatment across all groups that reach L periods of exposure before this underlying date. So what is underlying T is the last time period where you still have at least one group that's untreated. Why do we restrict attention to groups reaching their L period of exposure before that date? Well, that's just because after that date, everybody is treated. We no longer have any valid control group, and we can no longer identify treatment effects. Okay. So of course, if you have ever treated group, then this lower RT date just the last time period in the panel, but all really get treated. If let's say at period 4 everybody has been treated, then underlying T is period 3. Okay, we have this connection between the ATT and ATTL. The average on the treated just a weighted spread of effects being treated for 1, 2, etc. years, with a weight proportional to the number of groups for the effect L periods of exposure can be estimated. Okay, so even in very standard design, we have that if we don't impose any assumption on treatment effect heterogeneity, this event study function cannot be used to determine if past treatments affect the outcome, etc. Oops, sorry. So now let's rule out, actually, let's assume that we don't have any dynamic effects. Your outcome only depends on whether you're treated today or not on whether you were treated yesterday. And let's assume that treatment effects do not vary over time. Okay. Under those, in the classical designs that we had considered earlier, we would have ATT1 is equal to ATT2 is equal to ATT3. Treatment effects don't depend on your path of treatments, and the treatment effect won't change over time, so your effect is not going to be changing over time. Now, and staggered, we could have that, let's say, ATT2 and ATT3 are different, even without dynamic effects or without time varying effects. So why could that? Yeah, exactly. So now we have a third that we have compositional changes. So this ATTL effect only applies to groups which are observed L periods after first treatment before the end of L, for instance, and as L for such group. Okay. So that's a further caveat that arises when interpreting and study graphs. You can't really know whether the change in the effects are due to dynamic effects, time varying effects, or compositional changes. The good news about last sort of difference between the ATL effects is that that is to control for. You can just redefine your ATL effects in a way that at least up a certain L effects are instead for groups. Okay, and some, no, if all, but some of the developed comments that we're going to talk about are to make sure to neutralize conditional changes. Okay, so first we're gonna do a bit like we did chapter. We're gonna first do the static two-way fixed effect estimator in those binary and stacker design. Then we will talk about two-way fixed effect event study estimators before moving to heterogeneity robust estimator. So two-way fixed effect estimator is still a coefficient of DGT in an OLS regression of YGT on DGT and group and time effects. And so paper with Xavier, we have a decomposition result for two-way regression. So first, we need to introduce those WT weights, which are equal to those regression USD divided by the average of those residuals across all the set. And those regression UGT, they are just the residual set from a regression of on group and time effects. Okay, so UDL, you would take this indicator that's equal to 1 if AG has a UDL at T, and you would just regress that on a set of state effects and the effects, and you would compute the residual from that regression, and that would be your UAT. Okay. So we have the following result. We have that the two-way estimate is unbiased for this quantity here, which is a weight sum across all the GT set of their different effects multiplied by those WT weight. Okay, so could someone try to interpret this result in general and in the context of the UDL example? Yeah, exactly. And so what is the condition to the WGT satisfy to get that bias for the ATT? Yes, okay, that's true actually, but that's like a more obvious condition. Hmm? Hmm? So the weights add because that's always true, because you see if you sum those weights across all treated sets, you're going to get the same thing in the numerator and denominator. Okay, so they always sum. But what? Yes. Hmm? So have negative weight, then that theta v identifies the A. So, but what beta identifies the ATP? So if you compare, yes. Let me go back to the definition of the ATT. So if you compare the definition of the ATT and what beta is unbiased, what's the difference between the two expressions? Yes, so should have put them next to each other. Yeah. What's the difference between this? The weight. The only difference. Okay. So if the weights are equal to 1 for it, then you're fine. You're quantifying the okay. And unfortunately, the only case where the depth weights are all equal to 1 is if you are in this design with a binary treatment, no variation in treatment timing. Okay, as you leave that, then you're no longer estimating the ATT. You're estimating this weight sum of effects. And of course, that's if you're ready to make non-anticipation and parallel trend assumption. If you're, and we're gonna go back to your comment earlier. If you're ready for assumption, then you can recover ATT. Okay, so the weight sum to 1 is already, which is a nice property, because then if the treatment effect is constant, if the TGTs are all equal to some real number delta, then you're fine, because expectation of that becomes delta times the sum of weights, 1, so you're unbiased for the constant treatment effect. Now, the truth is that constant treatment effect is often impossible. The example, you can argue that conservative liberal states are not have the same effect of unilateral divorce laws. Okay. So now let's look a little more at the weight. So actually possible to show that. So remember that so UAT comes from a regression of DGT on group X and time fixed effects as the residual regression. And so the residual actual value as predicted value, of course. And for all the treated cells that enter to our sum of effects, the DGT is equal to 1. So actual value of variable is 1. And then the predicted value, when you can show that DG dot plus D dot minus D dot, where DG dot is the average of across all time periods. So for instance, if you have a group that's always that is 1. That D is the average at period. You have a time period where half of the groups are treated is 0.5. And that is the average of group every time period. So why? So for regress TGT on group fixed effects and time fixed effects. So part of the regression gives you that TG dot enters prediction. So that's efficient on each variable. Yeah, group fixed effect. D dot is the time fixed effect. Okay, so that's all we are saying here. Okay, and so it's only if so now that we have the weights are equal to 1, we need D dot and D dot to be constant across all treated groups, and that's actually only going through here the classical design without variation in treatment timing. Okay, so now coming back, you try to find an assumption such that if we add it to our non-anticipation and parallel trend assumption, we would have that beta at Fe is unbiased for the ATT. No, because that trend is what allows us to get rid of Y0 in our decomposition of the two-way effect estimator. But now we find something that ensures that weighted sum of effects becomes more interpretable. So that's going to be an assumption about treatment effects, not about counterfactual trends without the treatment. That's going to help, but that's not going to be enough. Well, actually, yes, no, that could, so that give us ATT, but at least that give us weighted sum of effects without negative weight. It's something we'll discuss in a few minutes. Constant treatment effects, but actually something a bit weaker than that. We could have heterogeneous effects, but if the effects are heterogeneous, but kind of random way, that, GT cells with effect upweighted are not different treatment effects than the cells with effects is downweighted, then we would actually be fine. Okay, and that's the question I'm writing here. We have a zero covariance between the weight and these specific effects. Then we don't need to worry. Our complicated weighted effects is actually equal to the ATT.
So it's going to be violated if, say, the early adopters or the early treated are systematically different from the later.
Yeah, exactly. Exactly. And so under which, we are, I think most or all are economists. Economic model into treatment, you have exactly that of phenomenon that early treated are not going to be similar later treated in terms of their treatment effects. Yeah, exactly. You have a Roy selection model. If people select based on gains, people who are the first get treated are the who have the largest treatment effects. Okay. Now, maybe economists tend to believe it too much economics sometimes. Maybe people don't always decide to select into treatment-based gains, especially in the time of, if you think of the definitive application of the 80s of Eschenfeld, for instance, where would be comparing the weight of people's cells into a training program. There shouldn't be a strong issue. If we think more of the definitive that people are running nowadays, where we are leveraging natural experiments, where it's a policymaker that's needing to treat a certain area, for instance. Of course, you can make this type of decisions based on outcome and outcome gain, but maybe that's the only thing they take into consideration. So, and there might be applications where this condition of no connection between the weights and the treatment effect might not be ex ante completely employed. But is this condition testable actually? So we want to compute the covariance between two variables, the weight treatment effects. So the issue is going to be that there's going to be one variable that we observe and one variable that we do not, which is which. Yeah, exactly. We observe the weight, fine. We just residualize our treatment and we're good. The treatment effects, we do not observe them. So then, how do you go about testing suggestively? Of course, it's never going to be a hard test, but how could you suggestively test assumption? Yeah, exactly. If you, based on contextual knowledge, you think that there are good reasons, for instance, treatment effects to be correlated with income per capita, then you could see if the weights are correlated with income per capita, for instance. That could be a way to test the assumption. So estimate the two-way fixed effects regression separately in groups of states where you believe that there the treatment effect is likely to be homogeneous. Yeah, absolutely. Or and more, you know, but it requires take an ex-ante stance on, those are in those, let's say, 5 subgroups of states. Now, understand that treatment effects are homogeneous or at correlated with which sites to get treated first. Yeah.
Do I need to take a stand, or like if I've just divided it into a bunch of groups and I'm getting differences, then it would suggest that it's not whole.
Okay, interesting point. So the idea would be to say, let me arbitrarily divide the population into any small groups of states, estimate two-way effects regressions separately in each group. But I mean, so what's for sure that what you can definitely do is if you completely homogeneous effects, then you can test that by separately estimating the regression for the say rich and poor states, and if the two coefficients significantly differ, then you can reject the null of constant treatment effect. The converse of trying to validate or an homogeneous effect assumption, this I'm not completely sure, but that's I need to think more about that. Okay, so that's the first bad news about this result, is that unlike in a classical design, two-way fixed effect may not be unbiased for the ATT when we have a binary and square design. Now, second bad news is that actually the two-way fixed effect may not even estimate a convex effects. Okay, we could have that the weight are actually negative, and that's inspecting the formula for the weight, so the denominator of you can show is always strictly positive. So the sign of the weight really depends on the sign of this expression, and you see that so this is positive as well, but this is going to be negative and this is going to be negative. So the sum of these two terms is greater than the sum of these two terms here, then you could indeed have some weights that are going to be negative. So which are the groups whose X are the most likely to be weighted negatively? Yeah. Yeah, exactly. So early adopters are the groups whose effects are most likely to be weighted negatively. Okay, and in fact, you can show that if you run a two-way effects regression with some groups that are always treated, then dg dot is equal to 1 for those. Therefore, and those things cancel out. So the weight now only depend on minus t plus d dot dot. And then you can show that because the treatment rate in a binary design is weakly increasing over time, then if there is a group that's always treated, there will be at least its period t treatment effect will be weighted negatively. Okay, so then what is if we want to reduce and perhaps sometimes eliminate the negative weight, should I think be rather controversial? What should we do prior to estimating our two-way fixed effects regression? A very simple trick. Yeah, and that's, I think, that's going to be a very uncontroversial recommendation. Even if you don't implement any robust estimators, at least get rid of the always treated groups, because so it will reduce or perhaps eliminate the problem of having a non-convex combination of effects, but also at a deeper level, those groups, you never observe them without treatment. So necessarily any type of, if you're trying to estimate that treatment effect, you cannot rely on a diff-in-diff method to do that. You must be relying on something else, which is I mean, then perhaps you're fine, resorting to conditional independence assumption, but it's just that then you're moving into a completely different type of identification strategy. Yeah. No. Yeah, not entirely. That's going to be case. Yeah, no, exactly. So so it is going to reduce and sometimes eliminate the negative weights problem, but it will also not do anything to the other earlier problem that you will still not be estimating the ATT. Even if it eliminates the negative weight, you will still only be estimating a convex combination of effects. Okay, that's better than a non-convex combination of effects, but perhaps that's not as good as estimating the ATT. Yes?
Always treated any different from the never treated? I mean, you can just redefine what treatment is.
Yes, you could, but then you're making a parallel trend assumption not on Y0 but on Y1, and which I think that in very complicated designs, not binary ones, making a parallel trend on Y0, Y1, all the potential outcomes, what you need to do if you want to use diff-in-diff to identify something meaningful. But in a binary and staggered design, you may not need to make this type of assumption. And parallel trend on Y1 means that it's imposing some restrictions on dynamic treatment effects. Actually, because you're assuming that all groups with treatment follow the same outcome path, meaning that the incremental treatment effect from going from 1 to 2 exposure to the treatment has to actually be some kind of homogeneous between groups. So there is, I think, a cost in terms of making these assumptions. Yes. Yeah. Exactly. Yeah. Actually, I think it's yes, very good point. So I like leaving omitting the very important caveats with pre-trans tests that have been highlighted by people like Jonathan Roth and Romerton and Roth. To me, like the logic of diff-in-diff is that you have an event that happens at some point, and the event could be treatment. You go from 0 or 1, but it could be a bit more complicated than that. And you observe prior to that event, you observe your under counterfactual, that's the counterfactual, without event. And then you can test whatever, you can test trend assumption on their outcome under that counterfactual. And so here, that creates, back to your point, that creates a dissymmetry between parallel trends on Y1 and Y0, because if at the beginning everybody is treated and then some people start being treated, you're going to be, because you observe the Y of everyone prior to some date, you are going to be able to placebo test parallel trends on Y0, while you cannot placebo test parallel trends on Y1. Okay, so what's the issue with the negative weights? Well, intuitively, we don't want to have negative weights, but more formally, then if some of the weights are negative, that may not satisfy all the no sign reversal property, which was I think invented by Small et al. 2017, which requires that if, let's say, the treatment effect is positive for everyone, then the expectation of your two-way fixed effect estimator should be of that. Okay? You could not have an estimator whose expectation is strictly negative while everybody has a strictly positive effect. And here I'm giving a very simple numerical example where let's just estimate 3 times the effect of cells in California minus 2 times their effect in Michigan. Then if in California they increase the divorce rate by 5%, but by 10% in Michigan, then if the weight 3 and minus 2, we could end up with a negative two-way fixed effect estimator, while actually UDLs increase the divorce rates everywhere. Okay, so now, we already think groups that are the earliest are the most likely to see their effects weighted negative. Now, looking at time periods, what are the time periods when we are the most likely to have negative weights? The last one, exactly, because now dt in the binary series design is weakly increasing with t. So it's really in the last time periods and that we are the most likely to see some negative weights. So when we combine, it's the treatment effects of the early adopters at the last phase of the panel that are the most likely to be weighted negatively. So now the weights might not be negative, and actually in many binary and staggered designs, it turns out that the weights are all positive. When are all the weights actually likely to be positive? Again, looking at this formula here. Yeah. They enter uniformly, but if they enter uniformly and everybody is treated, you will still have a d dot t that's equal to 1 that will net out is that. So it's really more about ever treated, and which makes intuitive sense. You have a true control group that ever gets treated. Intuitively, that should help us aid the treatment effect, and that's indeed what is happening. Because if treatment is relatively rare, then, for instance, if you don't have any time period where more than, let's say, % of groups are treated, then it's less likely that this will ever turn out to be negative. And similarly, you should not have groups that adopt poor on so like adding or so that's also very contrary. The fact that estimating so you take, for instance, you take, so no, I'm not going to go, if you take the data of Wolfers starts, if I'm remembering correctly, in 1956, but then you have 13 years before the first treatment date takes place. So you might be thinking, okay, those 13 treatment years, they're not very useful. I could actually start the data in 1968. Well, weights attached to the first action in the full sample and the second one in the restricted sample will not at all be the same. Oh, yeah. So actually, until which time are we? 10:40. Okay, perfect. Okay, so the diagnostic check, it's useful to estimate those weights. Even though weights are difficult, it's just about residualizing a variable. Actually, with Antoine, is now when he was a grad student at UCSB, we developed a Stata package. And so the basic syntax is two-way FE weights. Then give the name of your outcome variable, the name of your group variable, time variable, and the treatment. And then because the command can estimate the weight attached to many different types of two-way fixed effects regression, here we're looking really at the standard one. And so we indicate that we indicate that with this option here. And we were saying that, perhaps you want to suggestively test whether the weights are correlated with proxies for the treatment effect. You can do that by using the test random weights option, where you would put as a var list all those proxy variables which you think are likely to be correlated to the effect, and you want to see if they are correlated to the weights or not. Okay, so first application question. So I would like you to run the basic static two-way fixed effects regression of the divorce rate on state and near fixed effects and the UDL treatment. We want to weight the regression by state population, and we follow the standard recommendation of Bertrand Nathan of clustering standard errors at the state level. Yeah. Well, I mean, it's going to be always like a type of tricky judgment call to make, but yeah, I mean, then there would be less indication that you need to drop two-way fixed effect and move to one of the robust methods. And if you had plenty of negative weights and weights that seem highly correlated with things that predict the treatment effect. Now, I mean, I know that I'm hearing a lot from applied researchers that now referees are asking for the heterogeneity robust estimators almost no matter what, even when you're in a design with no variation in timing. So, but whether it, yeah, I mean, most likely in this type of situation, you would then run the heterogeneity robust method and find that actually it's not that different from the two-way fixed effect one. Okay, so did I run the regression and can tell us if according to the regression, unilateral divorce laws have an effect on divorces? No. So the find a very small, so that's the syntax, and so the coefficient is small and insignificant. And we are going to compute the weight attached to a fixed effect coefficient in this regression. So first, we need to install the FE weight command from the SSC repository, and then the syntax is as follows. So you want the two-way FE weight to reproduce your weight X regression, except that you don't put e.state, e.here, because the command understands that and does not need the interaction operator. And then you specify that you want the weights for the classical two-way fixed effects regression. You specify that the way fixed effects regression looking at is a weighted one by state population, and then you want to test whether, so you could we could have looked at many different things, but one very obvious predictor of the treatment effect would be exposure length. We believe that treatment effects tend to grow, for instance, the more you're exposed to the regulation. Then we want to see if the weights are correlated with exposure length. Yes?
You need GT tools.
You need what? Sorry?
Sorry, you need some other package.
Yeah, which is installed.
Ah, okay, yeah. Okay. That's true. I remember. Mhm. Yeah, exactly. Yeah. So you get the same result. We did not start like a random tip generator that's going to give different results. Well, so sometimes until recently results not necessarily replicate because some weights are very, very close to zero. And different computers have different precision actually in terms of, so we had to say that below 10 to the power 12 or something like that is a zero. But,
So would it actually tell you zero weights on some of these?
yeah, because the weights are zero. It's just yes, Stata is not very good at computing. We now realize, and sometimes it makes these small computation mistakes and say that something is not zero while it effectively is zero.
But I guess when you're the output that says positive weights, negative weights, if there was some that were very close to zero, is your output actually going to have a third row?
So normally, it had about that. I think now the zeros are third actually. Okay, so we have a convex or almost convex combination of effects. Almost convex, because okay, we have a few negative weights, but so that's something that practitioners ask a lot. You know, how large should the negative weights be for me to start worrying? And there is, of course, not a good answer to that question. But here, if I'm remembering correctly, the weights are summing to something like 0. If I wrote that down, yeah, so to not even -3%. So intuitively, that's pretty small. Now, could it still be the case that the wave fixed effect estimator is biased for the ATT? Yes, because the weights are correlated with what? And like very strongly, okay? Like correlation is something like 0.7. So, and it's a negative correlation, meaning that we are upweighting. So almost effects receive a positive weight, but we're still upweighting the effects of a small number of years of exposure and downweighting the effects of a long length of exposure. Okay. Okay, so now let's start. So that's the result. Now let's start by understanding where those negative weights are coming from. And so for that purpose, there is a very useful result by Goodman-Bacon that shows that in a binary and staggered design, two-way effect estimators are weighted averages of two types of 2 by diff synthes. Okay, so those DIG, G prime, TT prime are 2 by 2 synthes that compare the outcome evolution of group G and G prime from period T prime to period T. And here, the weight entering this decomposition are all positive. So we are estimating a convex combination of 2 by synthes. And the weights are going to be strictly positive whenever G and G prime are stable. The treatment of group G changes from T prime to T, which in a binary staggered design can only be the case if that group goes from a treatment of 0 to treatment of 1. While the treatment of G prime does not from T prime to T. And that's where the issue is going to come from, because now there are actually two scenarios where prime's treatment would not change from T prime to T. The first is the scenario where that group is untreated at both. That's going to be, that's fine. We're comparing a group that goes from untreated to a group that's untreated at both dates. That's classical canonical diff, nothing wrong with that. But then the second scenario is a scenario where the group is actually treated at both dates. And so the negative weight in our position of two-way fixed effects regression, they come from this switcher versus always treated type of diff. And so here I've this simple example where which actually so if we do the history, so this is the result from Goodman-Bacon, but actually in for that Borussia and Jaravel had a similar decomposition, but in a simple example, and in an example that we're going to see now, where you have two groups and 3 time periods. And so we're going to assume that we have 2 patients who don't feel well. They go see their doctor. The doctor asks for lab. You have a patient who I don't know went to the lab a little bit earlier, so the doctor gets back the next day. But period 2, the doctor sees that the patient has an infection and they prescribe antibiotic to them, and the patient starts taking the antibiotic right away. And then you have the late patient who arrives at the lab a day. Unfortunately, the result is not there day 2. They arrive at day 3. At day 3, the doctor sees that the patient has an infection and prescribes antibiotics to them. Okay, so we have 2 groups, 3 time periods, an early treated group that's treated at day 2 and 3, a late person that's treated at day 3. So now we as econometricians say, okay, we have a research design, we have data, the two-way fixed effects regression. And if we do that, in that very simple example, the more general formula, the Goodman-Bacon simplifies to that formula. Okay, so in this example, the two-way fixed effect estimator is a simple average of 2 diffs in diffs. The first one compares the fever evolution of early and the late patient from period 1 to 2. And then from period 3, we're going to reverse the role of who's the treatment group and who's the control group, because on period 3, that's the late patient whose treatment status is changing, while the early treated patient, the treatment status is not changing. And we're going to take that's in diff here. Okay. So the econometrician is a bit puzzled because they find that the two-way fixed effect estimator is strictly positive. And they're thinking that they have made a huge medical discovery that actually antibiotics are not helpful, or that maybe there is something wrong in their method. So what could be wrong in their methodology intuitively?
The early guys have a reduction that's maybe larger than so basically antibiotics, yeah, so the treatment effect, that's more time passes, the reduction of fever is higher.
Yeah, exactly, and exactly, and that's why I'm using this.
Yeah, so
You're subtracting a very large dynamic treatment effect of this early guy. And that's why I use this example, because antibiotics, we all know that antibiotics are slow acting, and you need to be exposed to the treatment for several periods before they start having an effect. And so that's where type of caveats, these two-way fixed effects regressions are going to be very pronounced. Okay, so that's exactly what is going on. So we are going to do just a few equations to formalize this idea. So first, we have the first diff in diff, and that one is fine. We're comparing the early to the late from period 1 to 2. That's identifying the treatment effect of the early treated patient at period nothing, only other non-patient and parallel threads. Now we're going to look at the problematic diff in diff, and we're going to separate it into two parts. And so first, we have the control group in this diff in diff, which is the early treated patient, and we are looking at its outcome evolution from period 2 to 3. At period 3, the potential outcome we observe, the potential outcome with no treatment first, but then 2 period exposure. And at period 2, we are looking at an effect with no treatment first and then 1 period of exposure. And then, so most identification proofs, at least in this diff in diff literature, they all rely on the same trick, which is of adding, subtracting the untreated counterfactual outcome, and you do that again and again. And that's exactly what I'm doing here. I'm adding and subtracting this counterfactual outcome of the early group at period 3 without any treatment. And by subtracting it from this, I'm getting the treatment effect of the early treated group at period 3. And I'm doing the same thing at period 2. Okay. Then I do the same for, but now late treated group. The late treated group at period 3, 1 period of exposure, and at period 2, no period of exposure at all. So now make a counterfactual outcome evolution without any treatment appear. I just need to subtract, add and subtract that one here, because that one I already have it. And then I get the treatment effect of the late group at period 3. And finally, I get my DID N23 is this minus that. That term and that term are going to cancel under which assumption actually? So this is an outcome, that's the outcome evolution of the early treated patient without treatment. And that's the same thing for the late treated patient. Yeah, exactly. That's my parallel trend assumption. Okay, that's by me the fact that this and that are equal, and therefore when I take this difference, those terms cancel. And then I get this minus this minus plus. Okay. And so here you see you get that 8 versus diff in diff identifies a weighted sum of treatment effects where the weight comes to 1, because here I have a weight of 1, here a weight of 1, here a weight of -1. So weight sum to 1, but I have one effect, the effect of the early treated group at period 3 that's being weighted negatively. And finally, my two-way effect estimator is the simple average, this one here and that one here. And therefore, its expectation is half of this plus half of this. And when I put all the pieces together, I get that the expectation of the two-way fixed effect estimator has this expression here, which is again weighted sum of 3 effects with weights summing to 1, because I have a weight of 1/2, 1 minus 1/2. But where see that the one of the effects, the effect early group at period 3 is being weighted negatively, exactly for the reason that we saw earlier. And so the composition of the two-way fixed effect estimator in our paper with Xavier. In this example group, periods, the early and the late treated group, it reduces to that simple expression here. Okay, so that walks you from the, here we walked from the Goodman-Bacon decomposition to our decomposition in this simple example. Okay, and finally some graphical intuition. So, and I have a late treated patient, the early black and the late is in gray. The dashed lines are the counterfactual outcome evolution without any antibiotics. You see that without any antibiotics, everybody ends up dying. Their fever is monotonically increasing. And we are on parallel trends. So the parallel trend assumption is satisfied. And now you see also that antibiotic slow-acting drugs, after one period of exposure, the treatment effect is there, but not very large. And same thing, so, and that's both for the early and for the late treated patient. And the treatment effect becomes much larger after periods of exposure. And that's why, so the first definitive that's averaged by two-way fixed effect is a definitive comparing that evolution, and so it's slightly negative. But then the second one, definitive comparing that evolution to that one here, and that is very strongly positive because the early patient is now really recovering from the infection, and that's why we end up with a positive two-way fixed effect. Okay, so can you find an assumption on the treatment effects, TGT, such that under that supplementary assumption, we no longer have negative rates in our decomposition of beta F? The effect, so if they attenuate the right you can actually show that at least you don't have time reversal or something like that, which I mean, I would need to look more into it. I don't think anybody has made that point before, but something that would ensure that this definitive here now is an okay. Exactly. So yes. So two things. You need to assume that TE2 is equal to TE3, which is actually amounts to making two at the same time. First, no dynamic, being exposed to two periods rather than one period. All that matters is whether they exposed or. And then on top of that, you need to assume that being exposed today does not change over. Okay, so you're ready to rule out dynamic effects and also to rule out time-varying treatment effects, then you're fine. And I would not mentioning this result were only true in the two groups, 3 periods design we are considering. Actually, it's true generally in any binary and staggered design. If you're ready to assume that treatment effects do not change over time, then weight effects identifies a weight convex of with only positive weights. Okay. But that's only true in binary and staggered designs. When we're going to when you're going to move to more complex designs, even time invariant effects will not be enough to guarantee that way fixed effects identifies a convex combination of effects. Okay, yeah, let's stop here. Okay, so we will, yeah, of course.
Just a super quick thing that when you want to speak on microphone for questions, you switch it on so that the online participants can all hear.
Okay, so we were talking about this assumption that treatment effects do not change over time, under which in a binary and staggered design, two-way fixed effects identifies a convex combination of effects. Now, the last thing I want to say is just a quick word of caution. So, seeing that to determine whether or not a fixed effects regression identifies a convex combination of effects, people have been using the Goodman-Bacon decomposition, which gives you, for instance, the weight that your two-way fixed effect estimator puts on quote-unquote bad in diffs that compare a switcher to an always treated. Actually, there is not a one-to-one mapping between having a two-way fixed effect some weight on the switcher versus always treated and having negative weights in our decomposition. The two are not the same thing. And actually, the weights that the two-way effect is putting on switcher versus all diffs in diffs is always going to overestimate the negative weight in per decomposition. Okay, so you could have instances where actually we give examples based on real data sets. In the could have instances where the Goodman-Bacon decomposition tells you actually your two-way fixed effect is assigning 10% of the weights on diffs in diffs comparing a switcher and always treated, and then run our decomposition and it tells you two-way fixed effect creating a convex combination of effects. And the reason the reason for that is that actually there is not a unique way composing two-way fixed effect coefficient as a weighted average of 2 by 2 diffs in diffs. And the Goodman decomposition is just one way composing two-way fixed effects as a weighted average like this, but there are other ways. And we actually show as soon as you have pre-treatment dates, then you always have, you can always list another position than the Goodman-Bacon one that less weight on those bad sin diffs that compare to an always treated. So that's why that decomposition tends to overestimate the negative weights in the two-way fixed effects regression. Okay, yeah, so now, so a response to that those issues highlighted with two-way fixed effects regressions has been say, well, so if we make parallel trends assumption, then as soon as the design becomes a bit complicated and we no longer have binary treatment, no variation in timing case, things get very complicated. We identified weight sum of effects with potentially negative weights. What we would not come back to assuming that treatment is as good as randomly assigned. Okay, and in binary and staggered design, precisely what is that treatment timing is as good as randomly assigned. That the groups that it's as if we had been running an RCT where we had decided that I'm gonna mess up the real timing, but California had been assigned passing a UDL first, and then it was Michigan, and then it was Minnesota, etc. So if you're ready to make that type of assumption, then the negative weight here. Okay, so two-way effects is under a random treatment timing assumption, two-way fixed effects identifies a convex combination of effects. And that's a result that was shown by AT and Imbens. Now, there are, I think, 2 points that are worth making this type of approaches. The first one, and that's actually following work by David, that really to assume that treatment timing is as good as randomly assigned, then you should not be running a two-way fixed effects regression in the first place. Rather, you just regressing your outcome on controlling for the base outcomes prior to the treatment, because that's going to give you a more efficient estimator of the treatment effect. And the second point is that if you're going to start making claims that treatment timing is as good as assigned while you are in a natural experiment and not an actual experiment, then you should do what researchers running RCTs are doing in their papers, namely running an extensive set of balancing checks to really verify that indeed treatment timing is at 2000 baseline. And preferably, those balancing checks should also have been pre-specified, because you can always show me 3 balancing checks that work and don't show me all those that do not work. And so the idea that to solve the problem, just assume that things are 2000 baseline is actually gaining, to our surprise, some traction. We've decided to embrace that idea seriously in the book and to run this type of balancing checks in all the applications we read. And for instance, we do it in the Wolfers example, and we see that divorce rates pre-treatment, so treatment starts 69, so we have, and the data starts 1956, so we have 30 years of divorce rate data where nobody is treated, so Y0, 1. And so, in checks where we see if the treatment date, the treatment cohort predicts divorce rates before the treatment, and we find that they do very. So there is some indication that the treatment timing is not as good as randomly assigned in this application. Okay, so now the second thing that people have done in this type of binary and staggered design has been to estimate event study regression. Okay, so to generalize the regression we had seen in the classical design, so we are going to regress YGT on a set of fixed effects, set of period effects, and then have is relative time indicators that are equal to 1 when T group G has been treated for L period, where L runs from some negative value with the large negative value we consider minus K to positive values with the largest one being big F, and we exclude period 0 just before the event. And so a small variant on this regression is called endpoint binning, namely for first and for the last time indicator. You're going to replace those equalities by inequalities to bundle all the treatment effects or more periods of exposure to the treatment, and all the pre-trend coefficients for are at least K periods away from the event. So, okay, so as an application, we're going to start by estimating the event wave fixed effects regression on the Wolfers data set. We're going to follow the Wolfers paper by estimating 16 treatment effects up to 16 years per time. We're going to have 9 coefficients. We're going to have endpoint binning. And we're going to weigh the regression again by state population, and we're going to cluster standard errors at the state level. And so, question then for you is: according to this regression, do yields have an effect on the divorce rate? So are there effects of those unilateral divorce laws? Yeah, exactly. And so because you see those very large positive effects in the beginning, and then in the long run, what do you see? Negative effects. Okay, and so remember, the fixed effect coefficient was what actually the static model. We were finding a positive, a negative effect, no effect. We are finding no effect, and it's like, you know, these positive short-term effects were being compensated by the negative long-run effects. And actually, you're a thinker, because it took us quite some time to find a potential rationalization for why for the negative effect. That's, I mean, because then you can start having even more interpretation about how the labor market is, the mind market is working. But yeah, to me, that's like the most intuitive one would be to say people are more likely to divorce, but the people who are induced to divorce by the law are people who would have divorced ways. And so find a large positive effect, but because those divorces are just divorces that would have taken place later, you have a long-term negative effect. Okay, but there could be other potential. So that's like that's one potential explanation, but we're going to talk about other. So do our patient and parallel trend assumptions seem to hold? Yeah. How do you? How can you see that? Yeah, exactly. Exactly. Because we have 9 of them, if we want to be a bit careful, what should we do rather than looking at the coefficients individually? Yeah, exactly. And so if we do that, the p-value is actually very large. Okay. And because we don't discuss that as much as we should in this class, we also have the Roth and Rambachan and Roth critique in mind. We should not only look at whether the placebos are significant or not, but we should pay attention to the magnitudes. And here, relatively good scenario where the magnitude of the pre-trend are small. The pre-trend coefficients are also precisely estimated, so that even if I take the lower bound for my confidence interval for the first trend coefficient, and I extrapolate this trend, which, you know, this differential trend, which in truth cannot be out based on the data, even if I extrapolate that throughout the treatment period, I'm still not able to rationalize my actual treatment effect estimate. So that seems that's one application where at least the short-term estimated effects are kind of immune to that critique. Okay. So, but now, even after having said that, so those long-term effects, you know, the optimist explanation is the one I gave. Okay, this is real. This is a real treatment effect. We just induce some people to divorce earlier than they would have had, and then in the long run, we see the negative effects. An alternative explanation is that those long-term effects, they are all identified starting at 11 years, 12, etc., all the way till 16 years post-treatment. We are only able to test parallel trends for 9 years prior to the treatment, and 9 years prior to treatment, now the confidence intervals on our 3 trends start being pretty large. Okay, and now if I take the upper bound of my confidence interval, that's the differential trend over between treated and control states over 9 years that I'm unable to reject. I extrapolate that throughout the post-treatment period, and now you see that I could rationalize those negative effects just by differential trends that I am not able to reject based on my data. So the bottom line is that, yeah, we're pretty confident to say that there is a positive short-term effect of these laws. The negative effect, it could be that is real. It could just be also that those are differential trends in the very long run. Okay, so but are those way fixed effect event study regression thing to do the first place. So here we're going to turn to a result from Sun and Abraham, which, you know, we're going to need to take our breath before even stating because it's even substantially more than the result of the static regression. So they show that for positive values of L, so the coefficients that are supposed to estimate actual treatment effects of exposure of L period treatment, those at FL coefficients are biased for the sum of two terms. Okay, and we're going to describe those two terms in turn. So the first one is not going to be so surprising once we have seen the result for the static specification. So that's first term. So remember, we're trying to estimate, let's say, for equal to 3, we're trying to estimate the effect of having been exposed to the treatment for 3 years. Well, this first term here is a weighted sum of the effects of having indeed been exposed to the treatment for 3 years in group G, across all group G that we observe with 3 years of exposure to treatment before the end of the panel, and take a weight of those effects, weight WGL, that sum to 1, but that might, for instance, be negative. Okay, so that part of the result very similar to the result on static regression we have already seen. What's new and more surprising is second weighted sum here. So is a weighted sum across L prime from L and across groups of effects of having been exposed to the treatment for L prime periods. So in view of this result, do we have that the event study coefficient is going to be unbiased for the effect of exposure of L periods to the treatment? So let's assume that these effects of exposure of L treatment are actually constant, that all groups have the same effects of being exposed to treatment for 3 years. Okay. Then this is just a real number now. You can pull it out of the summation, the weight sum to 1. So that term is going to be equal. Okay, we're fine. But is it going to be enough to have that beta stat FEL is indeed unbiased or that effect of being exposed for L years? Yeah, exactly. So now we have what is called this contamination problem. The fact that event study regression, your coefficient that's supposed to make the effect of 3 years exposure to treatment is actually contaminated by effects 1 year of exposure, 2 years of exposure, 4 years of exposure, etc., etc. Now, the weight in this second condition here, they have the nice property of summing to 0. Okay, so then under which assumption are we going to have that second term vanishes? Yeah, exactly. If the effect of 1, 2, 4, 5 years to treatment are constant, then this second summation is going to disappear. And that's not very surprising, right? Like this even two-way regression is assuming constant treatment effects. If treatment effects are constant, then it's going to be doing a good job because that's the assumption you're giving it. So it makes it does estimation under those assumptions. But if the treatment effects are non-constant, then we could have that this contamination terms do not disappear. Okay, so it's actually not super tuition for where the contamination weights are from, but we're still going to consider one simple numerical example. So we're going to assume that G is equal to 2, T is equal to 4, so we have 4 time periods. We have an early treated group that gets treated at period 2, and a late treated group that becomes treated at period 3. Okay, and we assume that we estimate the event study regression with no pre-trans coefficient, and we have only 2 relative time indicators for having been treated and having been treated since at least 2 periods, 2 endpoints beginning. Okay. Then in that case, we can show that coefficient on the first relative time indicator that's supposed to measure the effect of being exposed to treatment for 1 period is again a simple average of by 2 distinct diffs, where we compare the outcome evolution of the early and late treat group from period 1 to 2, and then the outcome evolution of the late group from period 2 to 4. So we're gonna make the same assumptions that the event regression is doing. So it's doing point binning. So rather, in principle, we could have included a relative time indicator for 1 period of treatment, 2 periods of treatment, and 3 periods of treatment. We are not doing that. We are binning 2 and 3 periods of treatment. Implicitly, when we do that, we assume that being treated for 2 or for 3 periods is the same thing. Okay? Beyond periods of treatment, you no longer have dynamic effects. So we make that assumption as well. We're going to assume that the effect of being treated for 3 or for 2 periods is the same. So let's parametric definitive is going to be this one. Okay. So what happens between period 2 to 4 or and late treated group? So early treated group start treated at 2. Okay, so at period 2, it's been exposed for 1 period, and at period 4, it's been exposed 3 periods. But actually, we are assuming that the effect of 3 periods of exposure is the same as the effect of 2 periods of exposure. Okay, then so therefore, so when we and that early treated group is our control. So when we're going to look at outcome evolution of that control group, well, it's going outcome evolution will have the effect of periods of exposure minus the effect of 1 period of exposure. For the late treated group, at period 2, it wasn't treated, and at period 4, it's been treated for 2 periods. So for that group, we only get, so baseline, we have nothing, and in the end-line period, we have an effect of 2 periods of exposure. Now, we make our assumption that 3 periods of exposure have the same effect as 2 periods of exposure. So this TE3 actually the same thing as TE2. And minus here becomes a plus. So we are actually looking at the effect of 1 period of exposure in the early treated group, plus the difference of the effects of 2 periods of exposure in the late and in the early treated group. If treatment effects are between groups, if the effect of 2 periods of exposure is the same in the late and in the early group, which is implicitly assumed by the event study regression, then this thing cancels out. And eventually, this very intuitive period 2 versus 4 of the late versus the early treated group, indeed, under the assumptions we are feeding our two-way fixed effect event study regression, is actually a valid way to estimate the effect of 1 period of exposure in the early treated group. Okay, so here the goal is to realize that by the way we specify this regression with all these implicit assumptions we are making, we are actually allowing, making it okay to make this type of very strange comparisons that are being made. Okay, but now, of course, if treatment effects are heterogeneous, then this term here is not going to vanish, and that's how you see that we will indeed have that the coefficient on that the coefficient beta at 1 will be contaminated by effects of 2 periods of exposure to the. Okay, and this is with endpoint dimming because it's actually a bit, it's already a bit of a complicated example. But for people that might ask, you can also come up with example rationalizing why we have this contamination even without endpoint dimming, even though the examples become even more messy. So, okay, so that's the first key message of the Soon and Abraham paper. If you run a quick effect event study regression with heterogeneous treatment effects, then the coefficients that are supposed to estimate the effect of L periods of exposure to the treatment might actually be contaminated by effects of other lengths of exposure. Now there is a second important message from that paper that concerns the pre-trend estimators. What they show is that if treatment effects are heterogeneous, the pre-trend coefficients in two-way effect and study regressions can be very interesting to test the no-anticipation and parallel trend assumption. So give the formula, but in their paper. But what they show is that here we are not going to parallel trends and no-anticipation because that's what we are trying to test. But so if you do not make parallel trend and no-anticipation, the pre-trend coefficient in an event study two-way regression, they apply the sum of two terms. Okay, the first term is doing exactly what you have in mind, namely, it's comparing outcome trend of late early groups, even for the early groups treated, to verify that before the treatment, the early treated groups and the late treated groups are parallel trends. Okay. So that term that we're going to call A, that's what we would like and those pre-trends coefficients to do. But now the issue is that we're going to have a second term, and the second term is actually going to be exactly the same as these terms here. So you're going to have that the pre-trend coefficients, they are actually contaminated by treatment effects. Okay, and so then you have two terms, one that measures differential trends, the other one that's contamination from treatment effects. And then you're going to under parallel trends and no-anticipation, the first term will have an expectation equal to 0, but the second term is not equal to 0 in expectation. So that means that the pre-trend coefficients could differ from 0, even parallel trends and no-anticipation are satisfied. So you might like the null of parallel trends and no-anticipation, why effectively parallel trends and no-anticipation hold. But then you have the first issue that could have differential trends, but then the term A and B for some reason exactly offset each other, so that placebo 0 wrongly conclude that parallel trends and no-anticipation, while in reality you do not. Okay, so you can make errors both directions, and then those pre-trend coefficients become not very. So well, exactly for the okay, so so I think we could come, and perhaps we need to come up with an example like that to show that assuming homogeneous effects, a comparison of outcome trends of groups that are actually treated is that way to test for the assumption that without treatment the two groups would have the same outcome evolution. But yeah, but I would need to. That's a good question. But I guess it's the same intuition as we saw for the actual effects. Okay, so this so all so this decomposition here, the weights can be computed. It's a bit as the static regression. The weights are just function of some residuals, actually. And Sun and Abraham have developed a stata package that's called event study weights, whose syntax I'm giving here, that allows you to compute the weight attached to any two-way effect event study regression. And alternatively, and I'm mentioning it because we're going to be using it in the application, you can also estimate weights attached to an event study regression using our two-way weights stata command. And the syntax is going to be the same as before, except that now the FX treatment does not only have one treatment variable, it has many treatment variables. You have all of those indicators for time since treatment, and which should be included. So to decompose two-way fixed effects regressions with several treatment variables, we have an option that's called odd treatments. And the pre-trend coefficients are not status treatment variables because you don't expect any treatment effect in the pre-period, but they are kind of control variables, so they need to be specified in the controls option. And the only reason why I'm going to be using that command instead of one application is just this command has this test random weights option that we think is useful to test the weights are correlated with things that we think predict the treatment effect. Yeah, and they should, unless there is a coding mistake on our end, they should be exactly the same weights. Yeah. Yeah, but that's actually like it's becoming another a point of distinction between the commands, the time also, because they don't have, or even so some of them compute exactly the same estimators, but use different methods to do that. Be faster or slow, and the options that go on top of the basic estimation routine. Okay, yeah, so let's do that. Or let's use two AFE weights to decompose the first event study coefficient in the regression. So that gives you a lot of output to read and to try to make sense of. And this is just because you could switch you could do the same decomposition for beta 2, beta 3, etc. So which would give you, so each of them you information on, if I'm not mistaken, 15 sets of ways you could do, so it's 16 to the square. Like, so, you know, perhaps reason to skip that altogether and move to the heterogeneity robust estimator, not without to understand what the E2 effects regression is doing. So the yeah.
How much far ahead do you want to sort of assume that the current term assumption goes, and is it so very common to?
So it is very common, and so in fact that I skip, but which is very interesting, which is that if you have if you do not have,
For example, the negative effects of the workers study. If you had been, you might not have had this negative effects.
you could have yeah, if you had been that 7 years, then you would have been conflating the still positive effect after years 8 and 9 and all the negative effects thereafter. So yeah, of course you're making a pretty strong assumptions there. But so that's a very interesting result from the paper of Borsak et al. That actually, if you do not have never treated groups, then endpoint binning is necessary. The event steady regression is not identified, and not identified like in the stats 101 sense, like the EXX prime matrix is not invertible, and just the and then you really need to, if you want to run that regression, you need to point binning. Now, point binning is already better than excluding altogether. So, maybe you observe some groups all the way up to 20 years after treatment, but you only include indicators for having been exposed to treatment for, let's say, 15, 16 years, and then you don't do anything. At least, so implicitly, if you do that, you're going to be assuming that the treatment has no effect after 17 years of exposure. With endpoint binning, what you're assuming is that the treatment effect stabilizes, not changing after 16 years. But
what about dropping those so you have the unbalanced panel?
Drop. Well, then you're back to your most likely, I would say. I don't know that this result. I'm pretty sure this result also holds in balanced panel. You could be, if you drop those observations after 17, 18, 19, and 20 years of treatment, then I think you need to, for the regression to be identified, you need to do the endpoint binning within the sample that you have left. You need to have been 15 and 16 together for the regression to be identified.
If you don't have an
If you don't have it. You do have an ever there. We avoid that. That is, we're just doing a specification of. We're not fully following it, but because so there are differences are on the specification in the paper. In the specification in the paper, there was no pre-trend coefficient. It's a 2000 paper, so referees were not at that point asking for pre-trend tests, apparently. And then so he looks at effects all the way until 16 years of treatment, but beginning years 1 and 2, 2 and 3, 4, etc., and then lumping all everything after that. So yes, but no, you're right. In that specification, we could actually have estimated the whole thing.
But I guess is that something you'd recommend? Like, if your choices are bin, drop, or
so first, so yeah, so if the choices are drop, bin, or if you have an ever-treated group, I guess I would recommend estimating everything. perhaps not showing everything with the argument that, or perhaps show everything, but don't pay too much attention if the last estimated effects become, don't pay too much attention perhaps to the last estimated effects, which can be in practice extremely noisy, okay, because they're estimated out of a very small number of groups, and but yeah, that's probably like the best practice. Okay, okay, so those so this coefficient estimates a sum of terms. What about the first one? Is it a complex combination of effects of 1 year of exposure to treatment? Yeah, we only have positive weights there. Now we see that, and that's why it's useful to have this option. We see that those weights are actually actively correlated with the year variable. So that this beta at 1 coefficient is upweight the effect year of exposure of the up group and downweight effects of 1 year of exposure to the late group. So if the effects of year of exposure differ for the up the late, then this first weighted sum, even though it's a convex combination of effects, it might not estimate 81 average effect of 1 year of exposure. And then we have the data where we have 15 terms. And so first one is a weight sum of 29 effects of having been treated for 2 years, where the weight sum is 0 and are small. Okay, so do a little bit of our coefficient that's supposed to estimate the effect of 1 year is a little bit contaminated by effects of 2 years of exposure, but weights are not that large. And then we have contamination from effects of 3 year exposure, with again weights coming to 0 and pretty small positive and negative weights, and so on and so forth. And at the end of the day, even when we take the sum in contamination term, the positive and negative weights remain relatively small at 0.06 and minus 0.06. Okay, so at the end of the day, the study regression is not too far from estimating a complex combination of effects, and there is a bit of contamination, but it does not seem too strong in this context, probably because in this, there is a big group of states. Almost half or 40% of the states remain untreated, which following the intuition that we saw static case is actually typically a good thing. Yes. So there is no good rule. So in the help file of the data command, we try to give a bit of like some rules. But, so one measure that we had come up with Xavier was of course, so let's get back for a minute to the static regression. Of course, if we have constant treatment effects, then the weights, be them negative or not, are not a problem. The weights are only a problem if treatment effects are heterogeneous. So we have derived this concept of the minimal standard deviation of the GT specific effects, such that you could have that your weight fixed effect is of a different sign than the average treatment effect on the treated. But in some sense, it's just moving the question, because now the command is splitting you a minimal standard term such that in real trouble, how to interpret that standard deviation in practice is never all that easy. But my and perhaps that's actually something on which it's kind of an empirical question in a sense, like, do we when some will have the current being done a systematic meta-analysis of 52 effects papers and compare them to heterogeneity robust estimators, will we find that the sum of negative weights is a good predictor for the bias of the two-way fixed effect estimator? And if so, is there like, I think it's mostly an empirical question. And what we're going to see is that last application that we will read in the chapter is that you can have example, all the weights are positive, and yet weight fixed effects is very biased. So having negative weights is probably even worse than having positive weights, but you can have weird positive weights that make your estimator pretty far from the ATT. Okay, good. So we can start. So we're going till when? Till 12:45. Okay, perfect. To 12:45. Yeah. Okay, so now we're going to review in turn the various heterogeneous diff-in-diff estimators that have been proposed for binary and staggered design. So I'm going to introduce the estimators of Callaway and Santana and Sun and Abraham that have been proposed at about the time and that are in some cases actually numerically equivalent to each other, even though different versions estimators then differ. So first, target parameters. So I don't know what this thing is doing. Thanks, sorry. So in in those binary and staggered design, you can aggregate groups into cohorts that start receiving the treatment at the same period. Okay, so we're going to denote by big C our set of dates such that there is at least one group that starts receiving the treatment at date small c. And we're going to have lower bar the earliest adoption cohort. So for instance, if nobody is treated at period 1 and 2 and then a group starts getting treated at period 3, the earliest adoption cohort is 3. Then we're going to denote by y bar CT the average outcome of group C at period T. And for now, we're going to assume that we have never treated, and we're going to denote by y bar T the average outcome at period T across all the never treated groups. Okay, and we will see what we can do when we not have never treated groups. So the first series of target parameters that are defined by Callaway, Santana, and Sun and Abraham are cohort-specific effects. Okay, so the RL is going to be the average the of the difference between the average outcome for cohort at date C minus 1 plus L under the counterfactual where it's been treated for L periods, which is what has actually happened, minus the counterfactual where it would remain untreated throughout. Okay, and so with respect to the target parameters we had earlier, this is just a slightly more disaggregated version of the ATTN effects we had introduced. So before we had introduced effects of L period of exposure for anyone in L period of exposure. Here we're looking at more disaggregated effects specific to each cohort. So the indicator of that parameter that's proposed by Sun and Abraham is a diff that's comparing the C-1 to C-1 plus L outcome evolution. So we're looking at long in cohort and in the never treated groups. Okay, and they show that under quantification and parallel trends, this estimate is unbiased for the effect of C of treated for L period. So intuitively, why is it that unlike wave fixed effects and unlike event study regression coefficients, this is unbiased only under anticipation and parallel trends and without any homogeneous effects assumption? Yeah, exactly, and that's why it's actually helpful to understand where the problems from two-way fixed effects are coming from, because once we understand the problem, there is them. Two-way fixed effect could have also used, let's say, for instance, here we have been using any cohort that was treated before C-1 at the group, because treatment is not changing from C-1 to C-1 plus L. But now we've learned that we don't want to restrict heterogeneous effects. We should not be doing that. Yeah?
So in the formula, so we're taking averages of outcomes that might have very different sizes. Is
that might have very different sizes, but
so, you may have very few observations in one of these in order to compute one of these four numbers.
oh yeah.
So,
Yes.
so
Yeah. And so, in for instance of the Wolfers example that we are looking at, you can actually, perhaps you can do a tab of the cohort variable in one specific year, and you're going to see that there's going to be some cohorts where you probably have only one state. And so that means that those estimators are going to be very noisy, and in fact, perhaps they cannot even be consistently estimated because you have, I mean, like it depends a bit on the asymptotic you have in mind, but you could have a design where it's unrealistic to assume that pairs of cohort is actually going to infinity. So to me, that's why I prefer to readily consider estimators of ATTX rather than the cost effects, because I feel that many applications, those are very noisy estimated and inference is not going to be reliable. But that's not true. Like if you think of a county-level application and the rest of panel so that you don't have any adopted parts, there you have actually reasonably precise estimated effects, even for the cost-specific effects. Yeah. To that cohort, or to exactly that cohort that only has, let's say, 1 or 2 for which the effects are estimated. Yeah, exactly. But you could even say that the state level data in the US, even consider ATTF, where we're trying to use all of the treated and we still like the Wolfers example, and there's only a chance. So whether to invoke particular inference, that's not completely clear. So yeah, but there are that part of the book. But there are things you can do when for number of all groups is low. To a bit unsure as to whether variance estimators relying on asymptotic approximations are going to be reliable. And in fact, but actually, perhaps the main recommendation on that is to actually start by running simulations tailored to your own data. So if you are in a where you have 30 treated and 30 controls, you don't know whether that's enough for neutrality theorem in. Then by applications based on data, actually, not like drawing normals or whatever, and where you verify that the coverage of confidence intervals lying on whichever standard you're going to be using indeed have nominal or close to nominal coverage. Yeah. Yeah. Okay. No, they are not, because we are assuming. So, not, but we're gonna maybe let's differ by a couple of minutes because I won't have ton of things to say, but I will have a few things to say about that in a few minutes. But you're right. Stage, it is true that with variation in timing, anticipation effects become more of a concern than without variation in timing. That's definitely the case. Okay, so now if exactly for and we just discussed, we worry that those parameters can be very easily estimated. Also, so of noise, there is a further issue which I think is important to keep in mind, is that when you start estimating those very aggregated effects, you also run of multiple testing actually. So because maybe you find that some cohort there is a significant effect, but it could just be a type 1 error. But so if for all those reasons we prefer to estimate more aggregated effect, then once we know how to unbiasedly estimate that one here, well, then we know how to also unbiasedly estimate that one here by just replacing that quantity by measure. Okay. Okay, so now the pre-trans coefficient. So we can not only estimate effects of exposure treatment, but we can also test differential trends prior to. And to do that, we can propose pre-trans estimators that are going to mimic the actual estimator, but instead of looking at outcome evolutions after the treatment, we look at outcome evolutions from C-1 to C-1 plus L for negative of L. So we are actually going from into the past with this type of placebo. But apart from that, we're comparing again groups, the core T and the N core. We're comparing the outcome evolution over the same number of periods and the actual estimator over L periods, but we just do that prior to treatment. And then to mimic our estimate of ATTL, when we can just take a placebo cross cohort. The only thing to keep in mind that the placebo of ATTL not perfectly mimic ATTL, because there are cohorts for which you can estimate their effects of 2 periods of exposure, let's say, but cannot estimate pre-trends of 2 periods. Okay, so for instance, if you let's say you have a cohort that becomes treated at period 3, you can estimate their of 2 periods exposure at period 4, but you can estimate 1 pre-trend coefficient for that cohort, not 2 of them. Okay, but up, and that's the actually that's the restriction that you can see here in the summation. But apart from that, we can construct a placebo that's fairly symmetric to the actual estimator.
Here, is there a recommendation on the size of the window to use for the free period, or because the longer you go, the more noisy it becomes?
Yeah, exactly. So theory, the more the better. So, and I think that that's also something that. So, I would say that the more flows you have, the more precisely estimated they are, then the more you can say about the actual estimators. You know, like an event study graph where you have 2 placebos and 20 effects. I think it's very important. Like perhaps that's the most you can do based on the data you have. But then I think researchers should be very transparent about the fact that the dynamic effect number 20 assumes parallel trends for 20 years, while in practice you can only test for parallel trends for 2 years, and therefore we should take with a stronger grain of salt all dynamic effects beyond the second one. And same thing, if your both are very noisy, it's it's not a reason not to know that, but again, I think it should, that's something we should keep in mind when interpreting the actual effects. Okay, so something that Sun and Abraham noticed is that actually all of the effect estimators and the pre-trans estimator, they can be obtained from a two-way effect event study regression. And this has two benefits. First, the pedagogical benefits to make it easier for applied researchers to understand that, okay, what you were doing was just a little bit wrong, you modify it in a very subtle manner, then you're fine, you robust heterogeneous effect. And there is a benefit, which is a computational benefit, that now we can rely on regression, which is very fast, and also gives us scanned hence estimators, etc., for estimation. And so the trick, well, the trick is just that rather having a single indicator for being treated for one period, a single indicator for being treated for two periods, you just interact fully those indicators for length exposure to the treatment with co-indicators. Okay, and once you've done that, then the coefficients in that regression become very equivalent to all those estimators we've been discussing, and therefore they are robust to heterogeneous effects. Now, what's tricky is that people in practice will often will perhaps not want to run this regression exactly as I've spelled it out. Maybe they want to include control variable in the regression. And now, actually, if you just include control variable in the regression, you're no longer guaranteed to have that's robust to heterogeneous treatment effects, etc. So that's the caveat to keep in mind. Because you're not controlling covariates non-parametrically, you're controlling for them in a regression way, namely in linearity, etc., etc. Yeah. So including controls, so that would not be a really good way to do that, but we're going to talk about, for instance, the Callaway-Santana method allows to include control variables. Typically, it's when you want to include controls, it's better to do it in two steps. To first estimate the effect of the controls on the untreated outcome, and then once you've done that, estimate the treatment effect. Yeah.
So you would want to include controls because there's might be issues with the parallel trans assumption. So
okay.
Condition on control.
Yes, very fine.
Because, I mean, the parallel trans is doing a lot of work.
Yeah. So it's a very good point. So what distinguishes differences in differences from a matching method that rely on conditional independence assumption is that there's going to be cases where the parallel assumption is plausible even without controlling for anything. Like your pre-trans graph shows that even without any control, you do have well, not very often the case, but you do have well that precise parallel trends. Then in that case, there is really no reason whatsoever, in my opinion, to include control variables. In fact, it's better to avoid it because this, then you enter into all those discussions as to which variables should be controlled for, etc. So it's only if you run your pre-trans test and find that without controlling for anything, you have differential trends, and then you should start thinking about control variables. And like you're using panel data, you have many different ways of controlling for things. One thing, for instance, is to include unit-specific linear trends or that type of things, which, in my experience at least, and my applied experience at least, are sometimes much more efficient to kill differential trends than controlling or whether a state is above or below median income or things like that. So to me, control, and that's why actually we don't really spend all that time on that topic. It's an important topic, but that's not the first order topic in definitive analysis, in my opinion, at least. Okay, so that's so the fact that we can do placebo test of no anticipation and parallel trends is the first way of answering your question. Say, yes, no anticipatory effects are more of a concern in binary and staggered design than in a regular design, but design without variation in timing. But at least we can run placebo check if indeed we have trends. Now a point that's going to be related to that point. So so far we've seen estimators that use never treated groups as a control. Actually, Clément now they propose estimators that are similar to those, but instead of using a control group only the never treated groups, they are going to be using all the groups not yet treated at the time period we're making the comparison. Okay, so for instance, in my C minus versus C minus 1 plus L, if where I'm trying to look at the effect of L exposure, rather than only never treated, I could use any group getting treated after C minus 1 plus L as the control. So now there's going to be pros and cons in terms of doing that. And actually, I'm only mentioning the pros, while what you just mentioned would be a con. So that's something I should add. So, but overall, I think it's a very extension for 3 reasons. The first one is that there's going to be many applications where you don't have any never, and then that allows you to at least do something at least until this period lower bar, which represents the last time period where you still have at least one group that's untreated, because that able to do definitive anymore. Then the second argument in favor of seeing the not yet treated is that you have many. I've seen that quite a few times where applied researchers have never treated and they also have variation in timing, but they actually discard the never treated from the analysis. The argument being that they only want average variation in treatment timing because they worry that the never treated are going to be too different from those that eventually get treated. I think that's probably a valid argument, but I think because when you do that, you can end up losing a lot of power if your never treated group is actually large. So before doing that, that's the same thing as for the controls. You want to do pre-trans test and verify that indeed the never treated are on completely different trends prior to treatment than everybody else, and then you have a good reason for not using them. And then the third argument for comparing the not yet control group to the never control group is that even if you don't worry about that being a bad control group, is just that it's going to give you a bigger control group, and presumably it's going to give you more precise estimates than if you only rely on the never treated groups. The only argument against using not yet treated, rather treated, is that anticipatory effects, never treated, arguably are not going to be subject to anticipation effects. Why not yet treated? Like if in your comparison you're using at period -1 plus L group that get treated in the next period, then maybe that group is actually the influence of the treatment via battery effect.
It's a bit of a philosophical question, right? Because you have a data set in a window. It could be that some of them not yet treated will eventually be treated, but you just
just don't see it. Yeah. But there, so on the mild assumptions like anticipation X are weakly thing in the distance from treatment that you're at, which sounds rather well, then there would still be an argument in. Yes, yeah, especially when the treatment was announced. I think it's actually very helpful, and in fact, then you can so it becomes a bit tricky by in timing. But assuming, for instance, that you have variation in timing, but you always have let's say a 2-year delay between announcement and execution. Then you redefine treatment as announcement, and then you interpret effect 1 and 2 as anticipatory effects, and effects 3 and beyond as actual treatment effects. When actually the lag varies, and it becomes a bit messy because effect the mixture of anticipatory and actual effects. But
But then, like when you do the beta L, like if there's anticipatory effect, you should see, no, that beta L minus 1.
yeah, up to important caveat that maybe maybe you have anticipatory effects, you're just underpowered to detect them. Yeah.
If you use the not yet treated as controls,
Yeah.
you cannot use the regression.
Yeah. Yes. Yeah. Yeah. Absolutely. That's
Yeah.
yeah. And the proving, and then I mean, actually, and that's why you need to do something else. It's going to be computationally more intensive. Like the Caraway command, much slower command of Sun and Abram, because Sun and Abram is just running a regression essentially. So. So they're computed by Bootstrap actually. They're computed by. Okay. So third, so actually we have proposed estimators that are similar to the Callaway and Santana one. So our main goal was estimators that are going to be applicable out of binary and staggered designs. So designs where the treatment can be non-binary, or in the sense that someone plans several changes of that treatment. The treatment could go up or go down, that type of more complex designs. So those estimators, they can be used, of course, they can also be used, of course, in binary and staggered designs. And is without covariance or weighting, they're actually equivalent estimators of Callaway when we use the not yet treated as controls. Okay, so to do things with control, Callaway Santana, they propose estimators that rely on a conditional parallel trend assumption. So they propose methods to control for variables. Or, I mean, Sun and Abram and our command also propose ways to incorporate controls, but that package is arguably the most developed in that dimension. And so, yes, so the syntax, because we're going to be applying those estimators now. So the Sun and Abram package is called study interact. And the syntax, you specify the outcome variable. Then you give all of your relative time indicators, variables that you would have included in your event study regression. And then you give the identifier of the group and time variable. And then to specify a core variable. So you need to construct a variable that's saying, okay, this group started getting treated at period 3, that one at period 5, etc., etc. You need to say which control group you want using. So they allow for two choices. They either allow for the never treated or for the last to be treated. Because if you don't have any never treated, but you still want to resort to their estimation technique that relies on regression, then you need a control group that's stable over time, and then the last treated cohort is a control group that's stable over time. And actually, one thing to pay attention to, because we actually messed up in a number of things, is that so many of those commands require specifying a cohort variable, but for some commands, for the never the cohort variable is missing. For others, it has to be equal to 0. Okay, and so you need to know which command does what. Okay, the Clément command is called csdid. Yes.
For instance, you don't have never treated, and the last cohort, you have very few observations, then solo never has to.
Yeah, exactly. That's I think a limitation. So you either need to have a big group of never treated or a big, but you know the big group, big last treated cohort scenario is much less likely actually. You know, like if everybody eventually gets treated, and you have and you have a lot of variation in treatment timing, why would I mean, it's a bit more unlikely. I think to me this command is more appealing in designs where you have never treated. Yeah. Okay, so yes, so csdid is outcome, and then you need to specify the time variable and the cohort variable. And then our command is called did multiple GPT, and it's outcome, group variable, time variable treatment, and then you need to specify how many dynamic effects you want to estimate and how many placebos you would like to estimate. And what we're going to be using in the application is that we have a built-in option to look at heterogeneous treatment effects, which is called predict at, where let's say you want to see if treatment effects vary along state income per capita, then you would be specifying in the var list income per capita. And the second argument here is, perhaps you're estimating 15 dynamic effects, and you don't want to have, in the first step, you don't want to have 15 heterogeneous analysis tables, and you want to only see if the effect of one period of exposure to treatment and 5 periods of exposure to treatment vary by income per capita. Then you can just specify 1 and 5 here, without having too many heterogeneous effects tables. Okay, so first we are going to type yes. Yes, ideally this would be a pretty principal rule, like to estimate as many placebos as you can, and estimate the corresponding number of dynamic effects. Yeah. Or if you end up estimating more dynamic effects than placebos, then flag that for your reader to know that, yeah, here I'm starting being a bit into uncharted territory in terms of how many, like I'm reading on assumptions that I'm not really able to test. Okay, yeah, so you need to install the interact package from SSC. And here, you're going to almost follow the syntax of your two-way event study regression. So that's the nice thing about this command, but with an heterogeneity robust estimator. Yeah, okay, so that's where I said it. So the core variable is missing for the never treated groups. There is an auxiliary package as well.
Oh, yeah.
Oh, and they don't.
So does the pattern of effects you get look very different from what you had seen with the event study regression?
Looks very similar. Huh? So no, what you so I plotted them on the graph. So you see here we see them side by side, the two-way effect and Abraham. They essentially paint the same story, namely no evidence of trends or anticipatory effects, pretty large positive short-term effects, and those more puzzling negative long-run effects. And so here it seems so we have two ways in that. Either we saw all of vision that wave effects seem to be potentially pretty robust heterogeneous effects because we did not have that many weight, and also the contamination, we did not have any negative weights, for instance, attached to this coefficient, and the contamination weights were not very large. So maybe that's why heterogeneity, robust, and two-way fixed effect are giving us the same results. Or the second explanation is just that the effects of PLs are not heterogeneous. And then if they're not heterogeneous, then there is nothing wrong with the two-way effect estimator. So a point I would also make is that, so usually, and I'm sure it's true in many cases, but people sometimes report that standard errors get much higher after using heterogeneity robust estimators, which is not very surprising. You know, you're relying on a more less estimator, so usually there are efficiency loss attached to doing that. But this example is actually showing that's not always the case. Like, in fact, it's not true. It's not going to be true for every coefficient. But for instance, the confidence interval for that one is smaller than the confidence interval for the two-way fixed effects regression. So it's a bit the opposite that we would have said. There does not be bias parametric estimator, but the parametric estimator does not seem to lead to any efficiency gain relative to the more non-parametric one.
So why did again, so this is the reason why the confidence interval for the green period looks different or more precisely estimated in the Clément than Santana?
Okay, so no, so that's because those. So here we use the default. I think at that really they even have the option. So those placebos are not at all comparable to those, and that's actually an important point to keep in mind. So default, so now they have an option, but the default placebos reported by this command are actually first difference placebos. So that means that this placebo and that one here for the first placebo, those are comparable. They're doing the same thing. But as soon as you look at placebos for two time periods, so one here is taking long differences from fg minus 1 before adoption to f minus 3, while that one here is taking a difference from f minus 2 to fg minus 3. Okay, and that's, you know, and if you think that potential out, you know, this type of standard error over time would be, for instance, consistent with a model where potential outcomes follow walk, so that longer the horizon over taking those long differences, the more the variance increases, and that's why that here as a much lower variance. Okay, but there. So to me, so that's actually a discussion that has popped up recently. So to me, it's better practice to show difference rather than short difference placebos. Again, with the idea that the placebos should mimic the actual estimators. Now there is in the event study context that we are at the moment, I think there is only one argument to also perhaps as a check complementary analysis also at the first difference placebos. It's just that visually it's going to be easier if what's going on is an anticipatory effect with the first difference placebo. Because if you really have anticipation just the last period before the event, what you're going to see is that this is going to be, let's say, positive and significant, while all the others are negative. Now, I mean, you know, long and short difference placebos are linearly dependent. You know, you can a long difference placebo is a first difference placebo. So you could also visually an anticipatory effect via placebos, because then in that case it would just flat the first one, but you know, I just find it a little bit easier to see if it's like something and then zero. But yeah, other than that, than small argument, I would say that yeah, it's probably better practice to always report long difference placebos. And yeah, I'm not, because for that one, then again, it's very different actually the way they do. So like there are many subtleties, and way pre-trained estimators are computed by all these comments are not the same, and so yeah. Okay, so then okay, before the break, let's just run. So let's install the CSD package. And we're going to estimate the same event study and placebo effects to make testing, because we're going to use the not treated control group, because otherwise it's exactly equivalent to the Sunana estimators. And yeah, the cohort has to be equal to 0 for the never treated groups. Yeah, the pattern is not bad. Some states are missing outcome data, but it should still be able to run out. Yeah, no, it's not running at all. So check you can go up to see your code. Maybe it's about the core variable. Maybe you equal to 0. No. Made that mistake several times, and I even released papers with that mistake. So,
sorry.
Switched yet. Exactly. Yeah, and that's exactly right. Yeah. It's going to have all the observations for which it's not able to compute a long difference. But actually, that's also an important point. That's not super well documented. You know, I mean, all of those tools are new, and but yeah, and so that's something to pay attention to. Yeah.
For the CSPID, if you're using only the not yet treated as controls, the reference are what? Like everyone's going to be treated, so they're comparing.
So my understanding on that, I need to actually, yeah, I thought for a long time that actually I need to go back to that paper to really make sure, because I thought what I'm describing here, except that you could replace the not yet treated there, but now actually I'm not 100% sure that this is indeed what the pre-trans estimators are. Yeah, but you know, you would like actually compare. Yeah, exactly. So it's treated yet, but you compare those that get treated in C to those that will not be treated in C minus plus L. Yeah, I think that's what the estimator, but I'm not 100% sure. So.
And here the same argument about, so C minus one, just using the one period three versus using an average.
Yeah.
That still holds, right?
That's
still have, potentially. I mean, they do only C minus one, but you could use an average.
You could average, but then that actually makes it harder to test parallel trend assumption, because if you use the entire average, and that's good, yeah, then you have. So that's something we discussed like Friday, like that perhaps you want 2 or 3 periods, but then some aside, yeah. But you know, like as said, even though our cross-sectionally trained brains tend to think that adding data is better, you know, in the time series context, and it's not clear that actually an efficiency gain with pulling more time periods. And then there is really no argument in favor of pulling time periods, because you're also losing in terms of testability. So. Should we, yeah, with perfect. So actually, so just comment on the results before we go for the only thing I wanted to say. So the results are the estimates are very similar, no big difference. And interestingly, the Sunana estimators are not much less precise than. In fact, there is no notable difference in terms of precision. So the fact of using a bigger control group does not to be in a big difference for precision here. And that might the fact that the estimators are very similar here could be due to the fact that we have a very big group of never treated states, 19 of them. And therefore, adding a few not yet treated change the results of that much. Okay, you after lunch. At what time exactly? At 2.
Okay, I think we're to start. If you want to meet in the hours with Clément, we are circulating a piece of paper that you can write your name for today and tomorrow. Please write your name if you want to meet with him. The other thing, if you want to use your mic, help a lot for the WebEx recordings. And with that said, I leave it up to the speaker.
Okay, so we're going to continue our discussion of all the heterogeneity robust estimators. So before lunch, we implemented that of Sunan Abraham and that of Calawa and Santana. Now we're going to turn to our estimator with Xavier, for which we're going to need to install the GTDIN package from SSC. And we're going to be estimating the same 9 placebo 16 dynamic effects as before. And we will use the built-in option for heterogeneous effects analysis I was mentioning earlier to test if the effect of 1 year exposure to a UDL varies by states population. Okay, and the argument that can be passed to this option has to be a time invariant covariate. So fixed population at 1968, which is the year, it's kind of the baseline population, the year before some states start passing UDLs. The states. So we're looking at whether more or less populated states have different treatment effects.
Okay, yeah. So the populations are incredibly small because it's like,
Yeah, because like millions. Yeah, absolutely. Yeah. So first, how does the pattern of pre-trends and dynamic effects look like? Nothing very different from what you had before. The feature of that command is that it has the f-test on the placebos already pre-canned, and so it's below the results table, and you can see that the null that all placebos are equal to 0 is not rejected. What's interesting is that heterogeneity analysis suggests actually extremely heterogeneous treatment effects, where the treatment effects are much larger for more populated states. Okay, coefficients are like David was pointing out. The coefficients are tricky to interpret. Those are the populations are in millions. We should rescale that. Still, the coefficient is very significant. And so, with respect to like when we made the point that the two-way fixed effect estimators and the heterogeneity robust estimators were very similar, that could either be because UDL's effects were homogeneous, or because the weights, the weighting embedded in two-way fixed effects regression was not problematic because it was correlated with the treatment effects. Then it seems to be the second option. Treatment effects seem to be heterogeneous. It's just that the heterogeneity of the treatment effects does not seem to interact in a problematic way with the heterogeneous effects. So actually, so the reason why we tested for heterogeneous treatment effects by a population is because there is a recent paper that actually I don't think we're going to be covering that section. So maybe I can give you the summary that shows that actually the effect of unilateral workflows are in the data set of Wolfers are entirely driven by California. Actually. So that's why we find that the effect so large is so correlated with population. When you take California out of the sample, there is no longer any effect of UDLs. And what they, even though it's a bit orthogonal to our topic, what they show is that actually in the same year that California passed the unilateral divorce law, it also passed a bunch of other similar type of progressive regulations around family law that could also explain the effect.
So if you go to California, you still get.
Oh, yeah.
And in fact, it just doesn't pass.
Okay, so I need to read the paper in more detail because but they say that all of it comes from California. Okay, interesting. Yeah.
So in this heterogeneity, you have interactions between the treatment status and the baseline population.
Yes, exactly.
But you also have covariate specific trends. So the idea of having
No, exactly, absolutely. So we are doing our heterogeneity analysis under the strong parallel trend assumption that all states are on parallel trends, and we don't need to allow to interact the trends by population. That's then under a strong parallel trend assumption. What we show in a paper with Xavier is that doing heterogeneous effects analysis is actually extremely straightforward. All you need to do is regress for the treated states. You just need to regress the long difference, those YG FG minus 1 to YG FG minus 1 plus L on the covariates. And that will actually identify, without taking any control group, that will actually identify whether the treatment effect varies along those covariates. While if you want to heterogeneous effect analysis, also the identifying assumption, replacing it by a conditional parallel trend assumption, then things become more complicated. Okay? And to us, there is no, I mean, the two things are a bit distinct. Like it's not because you want to do heterogeneous effect analysis that necessarily you need to move to a conditional parallel trend assumption. Okay, so yes, so we were talking about whether the Caravan Santana. So we've seen that the Sunanabra estimators, they have a regression representation. You can obtain them from a regression, and we were testing whether or not the same applies to the Caravan Santana estimator, and actually the answer is positive. So. And it's a recent paper by Dubé co-author that shows it. So first, they propose estimators that are very slightly different from those of Caravan Santana that can be obtained from a regression. Essentially, you regress, so they call their estimators local projection estimator, by analogy with the local projection estimation method of Jorda in series, and actually Jorda is a co-author of the paper. And so the idea to regress long difference of the outcome YGT minus 1, YGT minus 1 plus L minus YGT minus 1 on the treatment change, restricting the sample to either units that become treated at period t, for which dgt minus 1 is equal to 1, or units that are not yet treated at t minus 1 plus L, for which dgt minus 1 is equal to 0. Okay, and so this and also you add time fixed effects. Okay, so this is then a regression of this long difference of the outcome on a dummy variable, dgt minus 1. Dgt minus 1 is either 1 for the switcher, 0 everyone else. And some control, but the regression is saturated in the control variable. And then you can apply this to this type of regression, a result that perhaps already familiar with by Engris in the late 1990s, that if you regress an outcome on a treatment variable and some controls, but the regression is saturated in the control, then the treatment is comparing the mean outcome of treated and untreated units within each cell defined by the controls, and then taking what's called the variance weighted average of those comparisons. Well, by applying target to the AL regression, what L regression is doing is it's comparing the y minus 1, YGT minus 1 plus L output of units each at T and units that are not even treated at T minus 1 plus L. So we're comparing treated, not yet treated, like the Callaway estimator is doing. And the regression for period X, so this comparison T by T. And then the only difference, the Callaway estimator, so the Callaway estimator will be taking an unweighted average of this comparison. And now, once we do it in a regression framework, we're going to take a variance weighted average of comparison at each time period. But actually, Dubé show that if you essentially reverse near the way to undo the variance weighted average weighting in their specification, you can actually recover Santana okay. So some of you were looking for a regression specification of the Callaway. I think that's actually exactly what you need. So, stage of the estimator of Dubé and authors is that they are very fast to compute because they they rely on OLS regressions, and you don't need to bootstrap standard errors like the Callaway and Santana estimator. Now, that's the same as for the Sun and Abraham. All of those estimators that have a regression, a one-step regression specification, you need to be a little bit careful when you want to start controlling for covariance. If you were to naively just include some XGT into the regression, then that's not warranted to estimate a convex combination of effects. Okay, so that's the first family of heterogeneous robust estimators, those that rely on long comparison of long differences in treated and untreated. Now we're going to see a second family following papers by Prusak and co-authors, Gardner and Liu and co-authors. We start by presenting by following the presentation of Prusak or discussing the connection with the other two papers. So there are many different ways of obtaining Prusak et al. Estimators that are all equivalent, and each estimation method is actually helpful to gain some intuition on the estimation. So the first way of obtaining those estimators is to run a two-way fixed effects regression with many fixed effects, okay, with group fixed effects as always, but then with also one fixed effect treated GT cell. So that means that if you have 10 periods, 50 groups, and 100 GT cells that are treated, then you need to incorporate fixed effect for the groups, 9 for the time periods, and then 100 more fixed effects for each treated. Okay. So then to estimate the treatment effect in that period T, we're just going to use the coefficient in front of the dummy for that specific treated GT cell. Okay. And then if we want to estimate, so of course, that's going to give us even more disaggregated than the cohort-specific effects we have talked about. So here there is really, at least in the framework we are considering, there is really no hope that this will ever be a consistent estimator because it's estimated out of only one group. But with those as building blocks, we can then aggregate to estimate more aggregated effects. For instance, if we want to estimate a cohort-specific effect, well, we just need to aggregate all of our data at this specific effect or the relevant cohort, etc., etc. So, yeah?
Weighted, right, presumably by the number of, by how large the cell is or something?
If you want, exactly. If you think,
What do you mean by what?
no, but it depends on what is your target parameter. If you want to estimate the effect in the population of US states, then you don't necessarily need to wait. You could give the same way to the effect in California and in Arkansas. If you want to measure an effect for the population of US individuals, then you need to wait by the population. Okay, so why is it that this expression is giving us robust estimators in the sense that estimators that are unbiased only under parallel trend and no anticipation and without requiring some homogeneous effects? Yeah, exactly. So you see, like the first solution to the negative weight, non-robustness to heterogeneous effects problem was say, okay, we're going to need to take a deep dive into what two-way fixed effects are doing, understand what are the forbidden comparisons they're making, and then avoid making those comparisons. And another and perhaps simpler approach is say, okay, well, two-way fixed effect is not robust just because we write YGT is equal to alpha G plus beta T plus theta that's assumed to not vary be the same for everyone times DGT. If we want the regression to be robust to heterogeneous effects, we just need the regression model to be much more flexible and to allow for GT-specific effects, which is exactly what this regression here is doing. So, okay, so now many different numerically equivalent ways of obtaining the same estimators. So, yes?
The controls here are always never treated, right?
That's going to be the issue with this specification. So, as a regression, I don't know what it's doing exactly. So, and not going to be actually only the never treated. And that's going to be, but perhaps I'm going to defer that to by okay, so this regression has any fixed effects. Woolridge actually shows that if you're interested, instead of really interested in the GT-specific effects, really have a strong reason to be interested in because they are not even consistent. If you're fine with estimating cohort-specific effects, then you can run this regression here and get numeric equivalent estimators of the cohort-specific effects. So now, instead of having group fixed effects, this regression only has cohort effects. Then it has time fixed effects, and then it has interaction of cohort effects and the number of time periods treatment adoption. Okay, so we had a pretty similar regression formulation of Thun and Abraham estimators. So what is the difference between regression and the one that's the Thun and Abraham estimators? So maybe let me scroll back a few pages. Yeah, exactly. Actually, I don't need to scroll back a few pages. So yes, difference is that in this one, the Thun and Abraham version, L would take negative value, actually, because we would also be at the same time estimating pre-trends, which we are not. Okay. And I think this makes it clear. So you remember in the classical definitive design without variation in treatment timing, we saw, okay, we said, okay, to estimate the ATTL parameters, you can either run the classical event study regression or run a regression where take out all the period fixed effects for the pre-periods. Okay, and this function of this shows that actually the Soon and Abraham and Callaway estimator, they are actually equivalent standard way fixed effect event study estimators in a design without variation in timing, while the Boris estimator, they are equivalent to this estimator. We just put the pre-trend coefficients in the regression. Okay, and finally, the last possible method to obtain the same estimators is to use an imputation method. So there, yeah, to proceed in two steps. First, we restrict the sample untreated observations, all the untreated GT cells, and we regress in that subsample YGT on group fixed effects and time fixed effects. Okay. So we are estimating a two-way X model for the outcome, with attention to the untreated observations. And then use that regression to predict the counterfactual outcome without treatment of the treated cells. And finally, we estimate the treatment effect of each treated cell as the difference between its actual outcome and its predicted counterfactual outcome. And again, this will give you a numerically equivalent way of same estimators. So now, in large data sets, which method is going to be the slow? Which method is going to be the fastest computationally? Yeah, the fastest is imputation, because that's the method that has the fewest fixed effect. Okay, and even with very fast reg HDFE commands that we have days, estimating regression with fixed effects can be time consuming. So then the second fastest one will be this one, but that's actually, sorry, not necessarily true, because here you're replacing the core effects, which typically are fewer than the group fixed effects. So actually the fastness ranking is not necessarily the one I was saying. But what's for sure is that this one is the worst, because that's the one that will have the most fixed effects. So now another thing that becomes clear now is that because the difference between Soon and Abraham and Borosek et al. That in Borosek et al. We don't have trend coefficient the regression, then it's unclear how we can test pre-trends with this method. So what they propose is in their imputation version of their method, they propose to estimate the imputation regression of YGT on group fixed effects and time fixed effects in the sample of untreated observation, but adding leads of the treatment in the regression. Okay, adding a dummy for those GT cells that will become treated in the next period, or that will become treated in 2 periods from now, etc., etc. And then plot the lead coefficients. I mean, you can test the lead coefficient equal to 0 as a test of pre-trend. Okay, so we're going to implement these estimators. You need to compute the de-identification package from SSC. So, and the syntax de-identification outcome group time ID and first treatment, which is the period when a group first got treated. And now, for variable has to be missing for the treated group.
And most of these in the background, there's clustering is the state level and the group level. In the one, I guess the event study command, we had to specify the clustering structure, but not the rest of these.
They probably have clustering option. I'm guessing that at least for ours, the default is that cluster at the level, but you could cluster at a more aggregated level. Yeah, I think that by default they cluster at the G level. Yeah. So the estimates are shown here, and so again, the point estimates are very similar to those of the other commands. We run f-test that all the placebos are insignificant, and the f-test is not rejected. The placebos are very different from those of the other commands. In fact, so first, what normalization period is written here in this method. So because the way we do the preference test is by running two-way fixed effect among the untreated with 9 leads of the treatment, we decided to say that the period is actually -9 because everything is relative to, in some sense, relative to that amount of time prior to the treatment. And also, unlike with the other, especially the Caravan Santana, so it's only first difference placebos, but we have an option where you can use an option that allows to get long difference placebos. In each case, the placebos and the actual estimators are trick. Here, placebos and the actual estimators are trick. So, for instance, the type of formal reasoning that practitioners often do that. Okay, so here you see you have a positive pre-trend. So if anything, the pre-trends are playing against you and biasing downward your defect estimator. This type of reasoning you can no longer make it with the Borsiak et al. Paper because there is not the placebos are not the -1 of the actual effects, if you will. Okay, so now understanding the differences between the estimators and which one we use, if any. We've seen that in a design without variation in timing, so the estimators à la Borsiak et al., estimators à la Sunan Abraham, Callaway, and Santana are both unbiased, same assumptions. And unfortunately, the efficiency ranking really depends on the risk correlation of the errors, with the Borsiak et al. Type estimators being more high errors and less efficient is some walk error. Actually, the Harmon shows that the same type of conclusion still hold in staggered design. So even though there is, because it's always being never the end of complexities. So the first, the simple result that for ATT1, for the effect of one period, with random walk error, the blue estimator is that of Callaway-Santana and Sunana-Brown. Okay. Now, for long-term treatment effects, it's unfortunately neither Boisiac et al. Nor Santana estimator that the blue. Yet again, a third estimator, the B8 estimator, and I will explain what. So the H is for Harman and the B is for Pego and Quasser, who again, interestingly, have proposed the exact same estimator at about the same time. And their estimate is a diff estimator. So in spirit, I think it's fair to say that it's extremely close to the Callaway and Santana estimator, even though it's not exactly the same. So the idea is that Callaway-Santana, to estimate the effect of being exposed to L periods of treatment for a group that gets treated at date FG, they look at its FG minus 1 to FG minus 1 plus L outcome evolution and compare that to the not yet treated at FG minus 1 plus L. But actually, you can do a bit better than that. You can compare FG minus 1 to FG outcome evolution of that treated group to group not yet treated at FG, and then add to that first difference the first difference from FG to FG plus 1 of that group, that treated group G again, and the groups that are not yet treated at FG plus 1, and so on and so forth. And eventually, you're concatenating to get a lot of first differences with the exception of the last one, when we look at FG minus 1 plus L minus 1, FG minus 1 plus L, they have the same small set of control groups as in the Callaway and the Santana estimator, but for all the ones that we did, we have essentially bigger groups that lead efficiency gains. So now we look at this figure. Does it look like one heterogeneity robust is leading to substantially more precise estimator than the other? Not, no, with the exception, so there is this effect, the effect of one of exposure to the treatment is substantially more precisely estimated, the Boros estimator, than for the other. But actually, even though it's less close visually, the conclusion reverts look at other effects, and you can have, because of, like those intervals can be up % larger than the corresponding one for the command center. So it's not like a universal thing. Yes? This is very data specific, but in line is with the result that say that either way on the serial correlation of the errors. So for me, the recommendation would be to choose one heterogeneity robust method and not necessarily. I know that referees these days are see all of them. They are worried that people are going to be cherry the one that works best for their text. Yeah, I think that most cases they're going to be very, very close to each other. That's what we're finding here. There is actually, I saw another paper that does most comparison across 6 different data sets. In all data sets, two-way effect and the heterogeneous robust sometimes differ, but within the heterogeneous robust, very rarely see big differences. And if you do, then that's worrying, because that's an indication that your parallel trends and no-anticipation assumptions are violated, and you should not be using any of those methods. So I think that say computation time, it's probably more reasonable to just use one of those methods.
You need to put that in books.
No. Okay, so we have bias estimators, efficiency ranking unclear. So then, like I discussed this morning, the question is a bit, what happens to those estimators? The non-anticipation and parallel trends assumptions are violated. So what, and that's actually related to your question earlier. I'd say the downside of this estimator is that it's outside. So in the classical design without variation in timing, we are able to write it in closed form. Say, okay, this is a standard definitive, except that to construct the base outcome, we take the average from period 1 to f minus 1, but it's a standard definitive. Whenever a variation in timing, perhaps perhaps someone one day figure out a way to write this estimator in closed form, but so far it's not done. So if you ask me which type of comparison is this estimator making, I don't know. I can conjecture. Probably it's using all not yet treated to infer the trends, but I can't really be sure. And that makes it a bit harder to assess, which type of bias this estimator have, for instance, presence of differential trends, how it react to anticipatory effects, etc. All we can do is conjecture that what we saw in the case without variation in timing would still apply with variation in timing, in which case the Borussia et al. Estimator less biased if we have anticipatory effects, but more biased if we have differential trends that widen over time. Okay, so some other topics. So what we're gonna talk about is nonlinear models. So far we've only been talking about linear models, but you could be interested in a binary outcome or a count outcome, and you have a binary and staggered design. Want to run a probability regression or Poisson regression that would be robust to heterogeneous effects. And so in a follow-up of his 2021 paper, Woolridge proposed to use the same strategy that he had proposed, but for nonlinear. And so that means specifically, if we go back to his strategy for the linear models, that means that you run, let's say, a probit regression with cohort fixed effects, with time fixed effects, and with interaction of cohort fixed effects and relative time since you started receiving the. Okay. So with respect to this specification here, where we include group fixed effects, what's the advantage of only including cohort and not group fixed effects in the context of a nonlinear model? So do we have a potential issue when we run a nonlinear model with any fixed effects? Yeah, what's the name? Do you know? Yeah, exactly. So what was just some kind of computational trick to avoid estimating a few more fixed effects, algebraically equivalent but in a faster way estimate, actually becomes a very important idea in the context of nonlinear models, especially in context where you have very long panels, so that you don't have that many treatment cohorts. Then you have many groups per treatment cohort, and therefore you will need to include only two cohorts in the regression, and then that will be a way of bypassing the incidental parameter problem in the context of nonlinear models. Okay. So now there is so there are a few subtleties with with nonlinear models. The first one is that the no longer have a numerical equivalence between the imputation strategy, where you would estimate the model, two-way effect model, only on untreated observations, and then use that model to predict the counterfactual outcome of treated observations, and the strategy where you estimate regression with, you know, the cohort effects interacted this time treatment. And that's actually not something that Woolbridge discusses all that much in the paper. It does not explore what are the pros and the cons, because in the context of a nonlinear model, now you can do the both. You can keep you can take your untreated sample, regression with cohort and year-fixed effects, and then use that to predict the counterfactual outcome of treated cells, or the one-step estimation procedure. He does not really say what are the benefits of doing one or the other, so it's an interesting avenue for future research. So at an intuitive, and so here I'm only sharing a few conjectures, which might be wrong actually, but intuitively, this moving to a logic framework, this is still a little bit restrictive in terms of the assumptions it's taking on effects heterogeneity, because we have one coefficient for each C and L, but we are assuming that within cohort all have the same treatment effect. Okay, while the imputation where we start estimating a two-way model with no information whatsoever on the treatment, not going to be making that type of assumption. So perhaps when we start looking at this more closely, we will figure out that indeed, in the context of nonlinear models, it's a bit better the imputation strategy. Now, the downside of the imputation strategy is, so the upside of this strategy that just run one probability regression, so you don't need to worry, your standard errors are going to be computed by the software. While that strategy, because Woolbridge, I don't think drive the analytic standard errors, those estimators, you could actually need to bootstrap for estimation procedure, which can be actually pretty computationally costly for nonlinear models. Okay, so I think that's all I had for nonlinear models. Okay, so we're going to skip this, even though potentially important, weighting, estimating treatment effects, and we're going to discuss a second application. You know, like so we've tried to be a bit nuanced by not like unnecessarily instigating like too much fear applied researchers that they should never use two-way fixed effects, and that was the goal of this first example, Wolfer's example, where actually two-way fixed effects do exactly the same thing as the heterogeneous robust estimators. But now it's important to not draw the opposite and exaggerate the conclusion that never going to make a difference. And now we're going to see an example from trade where the heterogeneous robust estimators are pretty different from the two-way fixed effects one. So the application, the effect of trade agreements like NAFTA, the EU, etc., on bilateral trade. So the outcome is going to be the trade flow from country I to J at T, and the treatment is going to be an indicator for whether there is an RTA between I and J at J at T. And so now to map that, to map setting into our notation, you just need to think of an ordered country pair AJ as what we used to call before. Okay, so AJ now our unit of analysis. So type of a long time ago, people naively regressed the log of YT on a country pair fixed effect treatment, but then there was the very work of Silva and Tenrero who showed that it's actually better to estimate the Poisson regression by on those fixed effects, and the IGT. The reasoning being that the Poisson is going to be better if you have heteroscedasticity, and also because if you take the log, then you're getting rid of all the rows, and you have actually a significant, when you look at trade, you have a non-trivial number of country pairs that are actually equal to 0. So, and then there's any other, that's the literature that tries to be micro-funded and motivated by models. There's an argument that many control variables included in those specifications. You have, for instance, you need to put import area fixed effects and export area fixed effects. And also an important methodological innovation in that literature was to say that you should actually not exclude from the estimation cases where I is equal to J, meaning domestic consumption. Domestic consumption should actually be included in those specifications, and you have a micro and for that, then you need to have fixed effects for I is equal to J. Okay, so those treatments, they are binary and staggered. Researchers, literature are using Poisson two-way regression. So there is a concern that perhaps previous estimators might have bias due to heterogeneous effects. And so that's a concern that a recent paper by Cast and Yotov investigate whether findings from this gravity model change when you move from the standard effect regression to an augmented version that follows the recommendation from Wooldridge. Okay, and so they exactly follow Wooldridge, and so that instead of having a single and dummy, the regression is going to have a cohort times the times this adoption fixed effects, and then they will average the cohort times adoption fixed effects to have an estimator of the average effect on the treated. And they compare each Poisson specification to a standard one, the one that people have estimated. And they also estimate heterogeneity OLS regression and also standard two-way effect OLS regression. And so that's what they find. And so to run the standard two-way fixed effect Poisson regression, it says that having a bilateral trade agreement increases trade by 16.6 percentage points, while if you use heterogeneity Poisson regression, the point estimate more than double, to a bit less than 40%. And interestingly, what's really in this application, that might be not true in other things, but in this application, what in terms of methodology, what matters, accounting for heterogeneous effects, because moving from Poisson to OLS does not really change the coefficient that much, but in both models, allowing for heterogeneity increases a lot the estimated effects. And so to understand what is going on, they do a number of exercises. So first, they so those are estimates of average effect on the tree. They're pulling every length of exposure to a regional trade agreement, etc. So they look at 4 segregated effects, and they start by looking at effects according to length of exposure. And you see that are dynamic and increase a lot over time. And this pattern of increasing effect over time is more when you use an heterogeneous robust estimator and when you use a dynamic and eventually two-way fixed effects fashion. Now they also estimate average effects according to the year of a regional trade agreement. And see that while regional trade agreements that took place in the mid-1980s to the early 2000s tended to have very large effects on trade. All the regional trade agreements that took place for that actually had no effect on, or barely any effect on trade. Okay, so heterogeneous effects by length of exposure, heterogeneous effect by the option cohort well. So they have coefficients for each adoption cohort times length of exposure. So they fix the adoption cohort and they average across all lengths of exposure for a given cohort. So by the way, which makes me think, perhaps that's what you had in mind, is that there is this is a bit conflicting that in a sense, because for perhaps those RTA will end up producing a large effect, does that them for now?
So you should restrict the time period.
Yeah, yes. I don't know how. So, okay, but maybe just me who did not read the note, but close enough. That's what they did. So I want to. Sorry. Yeah, exactly. So that's perhaps, perhaps the reason why those earlier thoughts have large effects is just because for them the long run effects and so on. Like I mean, so assuming that their data seems to go all the way at least to 2015 or 16. So this 2001 cohort, we should be able to measure those effects that are being shown here. So I don't think this fully explains. This can explain part of it, but probably not all of it. Okay. Now, then the last thing they do is they apply they use our wave command, decompose their wave effect OLS regression, and so here in gray, see the way that the two-way effect estimator, that heterogeneity robust, put on effect of 1 exposure to treatment. That way puts on effects of 2 years exposure to treatment. And though here that the quote-unquote natural that one should put on the effect if one were interested in the average treatment effect on the treated. And so you see that way fixed effects regression up short-run treatment effects, down weighting and even sometimes weighting negatively very long-run effects. And then they do the same analysis by cohort, and you see that so it's a little bit harder, but if you look very close and see that two-way fixed effects regression is not putting sufficient weight on the treatment effects of the early cohort, and it's putting too much weight on the treatment effect of the late treated cohort. And so here, actually, the weight, there are negative weights, but not a crazy amount. The negative only come to -3%. But yet, because the weighting really interacts with this application with the heterogeneity of the treatment effects, that's why we find very different estimates when we use a regular method or an heterogeneity robust method. And finally, they do pre-trend, and they find that pre-trend estimates are small, and for the most part significant. When they run an F-test, they don't reject the null of no pre-trends. And here you see, so again, if we want to be a bit, if we want, so they are able to test trends up to 8 years for adoption. 8 years, we already have very significant effects of almost a 40% increase in trade. While when we look at the corresponding placebo, it's really much smaller. So it does. Here, an example where we have small, relatively precisely estimated placebo, so we can be fairly confident that we are, in as much as definitive go, we are credibly estimating the treatment effect. Okay, so left some conclusion. So far we've seen designs without binary treatment, no variation in treatment timing, and designs with binary treatment and variation in treatment timing. The bad is that we did a survey of the 100 papers published by the AR from 2015 to 19. So first, we found that 26 of those estimate a two-way effects regression, and that's not explaining that's not like including the theory paper, which not like presidential addresses or so it's like so those are very common. But of those 26 papers, we have retreatment, no variation in treatment timing. That's actually extremely rare, so that the baseline case that everybody has in mind, and only 4 more binary and staggered. So at this stage, even though we've already been looking for like 5 hours, we can only cover, this is the results we've seen, 6 out of 26 of the typical applications where basic effects regression have been used. And so what we will do in the next chapters, perhaps we won't have time to go to the end of it, but it will be to cover more design so as to have estimators that are more broadly applicable. Thank you.